Let's see, what other questions? So we can name an order. The first telescope wasn't built here, but we serviced it here. So hardware went through our facility, you toured. That telescope and the two that followed after it, both of which the other ones are getting built here. You can name those in order. Yep.
Planning, Hubble, James Webb.
What was the first one?
Planning.
Nope. Hubble. Yep. Hubble, Webb.
Oh.
Yes, perfect. Right. I'll talk about Hubble in a second. Yeah, so Webb was built in California by Lockheed Martin. We launched on the space shuttle. Goddard had responsibility for servicing. So all the instruments that went to Hubble went through the. You all see the big clean room on the tour? Yeah, so all the instruments went through that clean room. The astronauts were trained here with the hardware. When hardware came back, it sat in the clean room. And then Webb was actually built here, minus the telescope was built here, but the spacecraft that went on was Northrop Grumman, California. So we shipped it from here to Northrop Grumman. And then it went by barge to French Guiana, had a police escort because they're afraid pirates were going to steal James Webb. I don't know about the black market for telescopes, but who's going to put on, eBay? Hey, I think I got this telescope. Who wants it for $6 million? Obvious. What's that? Yeah, it'd be quite a sale. And then you saw roaming and integrated in the facility up there as well. So that actually got built. The entire thing got built here.
Where was the X-ray telescope?
What's that?
X-ray.
AXF was one that Chandra, those were, I think Chandra was TRW or maybe Lockheed. And AXF might have been, I don't know where that was built. Yeah, that was not a Goddard there. Goddard mission. We good? Can you hear us online?
Yeah.
Sorry, don't hit you.
Are you ready, Jacob, to do your?
I'm ready. So, hi, good morning, everyone. Welcome to day 3 of the Cosmic Capstone Challenge Final Showcase. I'm gonna skip some of this because I know most of us have seen it already for 2 days, but obviously this is what we're here for, is for any of the viewers at home, the students were asked to design a payload to be hosted aboard a, about 100 kilogram class satellite bus to demonstrate 3 more operations to provide an ICM capability on orbit. Yeah. Okay. So yeah, so I want to highlight a couple things. Is that we've really focused a lot on the mentoring this year. Every team had a mentor that they met with, like weekly or bi-weekly or whatever schedule worked for them. This is our second event. In December, we had those flash talks, and this is the final showcase. So we it's been awesome watching the teams the last 2 days. And I'm looking forward to day 2. A list of teams there. I don't think we need to go through that. That's what I was doing Sunday night to relax. And we do have prizes. We have at least 15 judges. I think so far we have 5 to 10 judges for every team. We're normalizing and standardizing the scores so that who wins and loses doesn't depend on which judge you get. We're going to send a survey out probably early next week. I don't know what the questions are. I said, we have to limit it to 10 questions and not make it too long because I know how that goes. But what we're looking for is, what would you keep the same? What would you change? And the other one I realized we need to ask is, what did you see amongst the other teams that you found really interesting? And there'd be some more questions along those lines as well. So I want to talk a little bit about next year. Next year, we're going to have the midterm showcase early December again, the final showcase. I haven't fixed these slides in 3 days. On the week of April 13th, we've already reserved the room in El Segundo. But what we're doing next year is we're broadening it. Instead of just one track, which is really doing something on orbit with a satellite, what we're doing is we're having several different tracks. So the first one's orbital manufacturing and assembly, and actually like at Arcasys, they've developed their interface control document and designed their bosun's locker basically to match this competition. And that's what they will actually use in the long run, right? Like they kind of use this contest as something to give them some focus for that. But that's a commercial service they're going to offer aboard their port. You guys can look it up. It's great. and they helped to put together some of this. The second one is lunar operations. This year we focused on orbital. We want to offer a track next year for lunar. We're likely going to require a prototype for that track. So teams that are really focused on prototyping, that might be a better one to aim for. Track theory of servicing. This is essentially taking an ESPA star or something like it, a satellite which can host multiple payloads, and designing a system architecture so that you can do servicing. You can take some of the ideas we saw here, like printing a patch antenna, like restoring batteries. What was the other one? There was, I know we're going to see one today on adding gyroscopes, right? Like you can think of different servicing functions you can do, design an architecture for that. This idea came straight from Lieutenant Zarek at the Space Force, who's a judge, and Andy Quas, who's a tech fellow at Northrop, who's worked on many of these programs. And the last one is in-space assembly from Greenfield Trin and some others on the Amartis team. But that's, instead of imagining a mission, it's more about think of the structures you could make with some of these automated assembly tools. Yeah, and that's it. I think I'll turn it over to the team at Goddard now, to Brian and everyone else, and Colleen and everyone else. Thank you.
Great. We're going to have Brian come up. Let me just share these charts real quick.
Well, she's getting upset. My name is Brian Roberts. I actually started off here at Goddard as an intern, sat in the same seat you all did many, many years ago. Graduated from Case Western Reserve University in Cleveland, Ohio, degree in aerospace engineering. Came here and then went to University of Maryland down the street to do research on robotics and space. It's the only university in the world that has a neutral buoyancy facility, so did tons of scuba dive with robots and simulate things in space. Got tied in with folks here at Goddard through a couple different avenues, and when time came for me to find an opportunity here at Goddard, I've been here as a contractor for about 7 or 8 years, and a civil servant 10 years last month was my 10-year anniversary. Civil servant. So you're looking to work at Goddard, especially nowadays, you ain't gonna get hired as a civil servant straight out. Very limited hiring, so if you want to come work for Goddard, we have tons of support contractors. Goddard's about a third civil servants like Danny, myself, and a few others, and most of the workforce, 2/3 of its contractors. So if you want to try to get a job, join as a contractor and then work your way up in a position up on civil serving, if that's what you want to do. So, I head up the ICAM office here at Goddard. It just newly formed here. We're going to formulate it right now. I'm the engineering director here at Goddard. With the folks here in the room. I'm going to talk to you about some of the ICAM work we do. Before we get started, I got one more pin. Who can tell me what OSAM or ICAM? Let's say, what was ICAM called before ICAM? Let's call it. I'll think another quiz.
You can ask what was it called even before that?
Oh, that's true. Yeah, you know what it'd be before. A couple different answers before that. What do we call before OSAM was cool buzzword and ICAM? What did we call that stuff we do? Close. No guesses. Satellite servicing. We just call it satellite. So Hubble, the group that formed Hubble kind of worked on that, the satellite servicing group way back in the day. The SSCO kind of passed around, had satellite servicing in the name, and then over the years we changed the name. So I'm going to tell you about some of the work we do here at Goddard, kind of in ICAM, OSAM.
I'm gonna let Jacob know. It won't let me share over the full thing, but there's only 10 people online, so I might just, for the students at least at Goddard, I'm gonna share it for us. It won't give me access to share.
Hey, I've just made you a co-host, so you should be able to now.
Okay, I was trying to figure it out.
So I have a quick door set up. Who can tell me what other facilities NASA Goddard
I think it
has
has to do with something with Chrome on my end. It's wanting me to restart because we don't typically use Zoom.
Yep.
If that makes sense. Let me try again.
We do some communication stuff out at White Sands,
I will
New
email.
Mexico, but, and then Blue one is out of
Presentation
Alaska as well, I think. We
to
don't know if we own that range, but we want to. Yeah. So the other one is, the only launch site here on the East Coast, you can go drive through from Greenbelt. Well, you got it. Thanks. What do you? So in Columbia, any fans of Seinfeld reruns? Tom's Restaurant that you see on the show is below NASA's called Goddard Institute for Space Studies, where we do climate modeling. While we launched used to be suborbital things out in the ocean to get effective students experiments, the Rock On program, the Rockset, I think it's called, you can launch on that if you have a chance, really cool. We now also do orbital launches. Northrop Grumman's been launching supplies to space station from all of them. So if you're ever here, it's a great place to go see a launch. You get really, really close, sometimes too close. The police will move you back. A really cool place to see. And I think Rocket Lab from New Zealand is starting to do some orbital launches pretty much from all as well. So if you're ever back on the East Coast, you can see the launches from here if they go off, at night, but it's a short drive about the short. Cool. Okay. You said on
Brian, how do I get to your email?
oh, what's that?
Can I get on your email?
Oh, email.
I'm just gonna send him the presentation.
Okay, cool.
Because your computer doesn't have access to it.
Oh, got it.
But it's all right.
Okay.
We're all good.
Another quiz.
Another quiz. One more quiz. Brian is full of quizzes.
Having another. What is the next launch? Goddard is doing. I asked them after some space station, but I don't know.
Who's gonna be, next NASA administrator?
Possibly. Who got nominated to be the following names? His first name? Yeah, Jared's his first name. Yeah. Yeah. What's special? Anyone know his background? He founded a couple of companies, made lots of money, went to SpaceX, bought 3 missions to fly, flew with his colleagues, raised a bunch of money for charities, and the second mission he just flew was last year, a couple months ago, went up and did the first spacewalk that wasn't a government-funded spacewalk. You see how the spacesuit popped out the hatch for a couple minutes, looked around, came back in. He had another mission planned to fly on a Starship one day, one of the complete to become some messenger after there. That's the nominee to do this. Not that.
Should be any second.
Yep.
You could start out by just explaining what I stand, because that's the first turtle.
Oh, sure. Yeah, I think hopefully you saw on some of the slides. So the reason we went from OSAM to ISAM, the O in OSAM was on orbit, which meant things in orbit. We wanted to serve satellite telescope stuff that we've been doing forever here at Goddard. But as you see on the table, we have things like modular instrument packages to put on the moon and things we want to put on other planetary surfaces. So we decided that OSAM was too kind of, specific to on orbit. So the O became I. That's where the ISAM orbit became. So it was kind of everywhere, or in space. Orbit. And then S in S in ICM stands for servicing, right? That's Hubble servicing, the various telescopes, servicing space station, things like that. The A stands for assembly. A couple of different missions NASA's had to do assembly in space, so you don't have to launch everything like with Webb, right? It kind of got folded up in the launch vehicle, and that's the biggest thing you can launch. If you want to find, aliens maybe in some other solar systems, way out in the galaxies, you need really large light buckets. You can't do that by folding up your telescope on a launch vehicle. So if you eventually want to assemble mirror segments, assemble boom segments, that was the idea behind the A. And then the M was manufacturing 3D printers in space. So that was kind of the triad. Launch all your raw materials, be able to manufacture things on space, have robots or whatever assemble them together. And then when you put these great light buckets in space or whatever you're doing and have instruments in there, just like how we want to launch the next greatest, instrument. Imagine your iPhone if you never change your iPhone out for the next 30 years. It's laughable. But we do that with telescopes all the time, right? We don't have ways to put things in satellites. The other thing we don't have the ability to do right now is imagine leaving Goddard here, you make a wrong turn, and you turn right instead of left at Greenbelt Road. If you were a satellite, you basically park your car on the side of the road and go buy a new car. You have no tow trucks to move things around. Or imagine you're like, hey, I made the right turn, but you're running out of gas at the the bottom of Greenbelt Road here. Again, if you were a launch vehicle or a satellite, you park your car on the side of the road, go buy a new car instead of filling it up. So that's the paradigm we're trying to change with ISAM, is have the ability to service things that use technology, change things out, move things around to save money. So we're not launching satellites every time. So that happens. Good. So the analogy is kind of, back to what I mentioned there, is the interstate system, right? Is we didn't kind of start off with all these great highways and service stations, right? The government established this idea of having roadways, and as we started getting highways between cities, people started deciding, hey, you can make money by, putting a donut shop on the corner here. I can put a gas station here and make money. So same thing we're trying to do in the government is, it's really hard for private investors to go out and make money on something that doesn't really exist, right? So it's really hard for someone to say, I'm going to create this infrastructure in space, send satellites and service them, and the investor's like, what are you doing? This doesn't exist. It's not there. It's really hard. A whole bunch of reasons why it's not possible. So the idea is the government can invest in that, buy down the risk of technology. You see some of the technologies here, right? How you refuel a satellite, what the valves would look like you put in there, right? So the government can do that, as we did the comm satellites back in the 60s, and then license it to technology to industry, and then you can create, anyone in the room can create triple in space, a gas station in space, come to the government, leverage the work we've done in the government, and license that at a reduced fee of what it would cost you to do on your own, and that'll create this kind of super highway in space, and then you can have depots in space you can get fuel from, with Space Force will connect. You can have places you might stash instruments to replenish satellites in the future. So that's kind of the idea behind what we're doing with ISAM, is create this national infrastructure that we can all be part of, which you're been doing as part of your project this year. Next one. And so this isn't just an idea, back in the day when we started Hubble here at Goddard, back 70s, 80s, it was really just Goddard doing this. Hubble was kind of the only thing we were servicing. Space Station came along, we did a little bit with that, but it was really kind of, individualized groups within the government doing it. And so a couple years ago, the White House decided that this is big enough, we're going to put out a national strategy for ISAM, OSAM. And you see the two documents here, you can download them, really great information in there. The first one was kind of the OSTP, the Office of Science and Technology Policy. And so here's what we want to do. And it wasn't just NASA, it was the entire government. Space Force has a role, Commerce has a role, right? Everyone in the government has a role in making ISAM possible in the future. And then a couple months after that came up the implementation plan. Who's going to do what, right? A plan's great, but you need to figure out who's going to do what. Who's going to referee when Air Force and Space Force and NASA say they want to do the same thing? Who's really in charge? Who's helping whom? That was what the implementation plan kind of put that strategy together for what we're going to focus on, how we're going to move out and do it. Cosmic kind of spun out of that, right? The work you're all doing kind of flowed down from this document that got put, which is really the first time anyone in the government's put out a strategy that kind of tied everyone together. We sat in rooms with our colleagues in the government and all decided what we're going to do. It wasn't just groups kind of doing things on their own. So it's really exciting that that's what kind of forced us all to get together and work. Next slide. So you heard about Cosmic, right? This is kind of the way to coordinate within the government, people doing ISAM, the folks in industry, folks in academia like yourself, right? It's typically the way it's done is academia, needs the right grants to get money from government. Government sometimes funds industry to do things. Industry wants to do things, and we felt that was inefficient. So it's really a way to get everyone together to figure out what are we all focusing on, share the same information. Even within the government, we realize there's duplication of efforts. Air Force is doing some of the stuff that NASA's doing. We don't talk to each other because we don't, the government's so large, we don't have a chance to interact. So Cosmic was a way to really pull all that together, and kind of the Capstone work y'all are doing was one of the spin-offs of that, making sure that there was a focus for some R&D and industry engagement, as well as universities get involved as well. So if you're interested in this work, when you do graduate, you can do this work in industry, you can come to the government. There's opportunities in the future to kind of keep engaged in that. So focus on the work we do here. Our group it's still used to be called Exploration and Space Services group at Goddard, where it was a group at Goddard that kind of coordinated all the servicing work getting done, the ISAM work getting done. Many different projects we had over the years. We do some low, what we call TLL, technology readiness level, which are things like, what does this valve look like, to go up and pull a cap off a satellite, right? So we'll start off with RP parts, put in a robot, we'll look at some basic things, we'll get feedback from industry and other places, we'll invest some more, and we'll, sometimes just do a lab demo. In other cases, you see there, we've actually flown things in space. So we, sometimes we'll just do stuff in the lab. You saw that on the tour. Sometimes that's good enough, and a company will come and say, great, I want to license that. Here, I want all the drawings. I want to know what you're doing with that. I'm going to go make it to do something that I want to do. Thank you very much, government. Other cases, we're interested in ourselves, so we'll actually fly things on in space. And so we've flown a couple different experiments on space station, a really great test bed, because the robot's already up there. We kind of have access to the space station. And so we've flown payloads, a couple different payloads over the time. One was called the robotic refueling experiment. In fact, we're on Jeopardy. And they asked the last payload ever launched on the space shuttle. It was RM, a robotic refueling experiment, about the size of a washing machine, and it had tools like this on it. You see some pictures of it here in the poster, and it's on the lithograph. So it had tools on the front face that the DEXA robot built by Canada that's up there servicing space station, right? So sending some astronauts out to place batteries and do things. Canada's contribution, like with the shuttle, contributed a big robot arm. On space station, they provided a big robot arm as well as a 2-arm kind of handyman robot. So it goes out and does things on space station. So we launched an experiment that basically is what you see on the satellites. On the side panel, you see things like blankets and fill and drain valves you put fuel in, and different things you might have to service, and then tools for the robot to grapple. So for the last 10 or 12 years, we'd have Dexter every 6 months or so. We fired up a little tool and demonstrate something, and we could simulate what we can't simulate here on the ground. Things like lighting conditions, right? We saw the room painted black. It works sometimes, but we've had issues where you don't quite get that perfect, and so your algorithms kind of look at the corner of the door like, oh, that's just the door. That's it's in space. You really want to focus on this other thing. So by doing things in space, we really get a sense of what it really is like to be able to simulate things on the ground and make our simulations better. The only thing we can't do, as you might guess, NASA does not have a zero gravity room. We have a zero gravity plane. You all can fly in Zero G Corp. You got $5,000. You can fly in a parabolic flight, or I think students can fly experiments on there as well. You can simulate zero G, but it's really hard to do that on the ground. So when we pull out cables and things, we get tricked on the ground because cables, kind of follow a natural, gravity field. And we sometimes been surprised in space when we, went and grabbed the thing and it didn't do that. So we now simulate things on the ground better. So really, it's like taking a quiz and an exam, right, college? You don't just take the final exam your first day. The class, you kind of do homework, and that teaches you what you need to know for the final. So the final exam for us is flying things in space. And so we've flown RM, a couple different payloads. We've done some cryo replenishment, some xenon replenishment, how you would take things apart, that sort of stuff in space. And then we flew a second experiment called Raven, which was basically a box about the size of a microwave that had computers and rendezvous sensors in it. And what we would do is every time a vehicle from Russia or Europe or SpaceX or Northrop Grumman would approach space station, we would have that thing track as it came up to get an idea of how well we could simulate things on the ground. Because again, you can't simulate the Earth limb on the ground, the Earth brightness, that sort of stuff. So it gave us a real life kind of experience doing things in space and made our algorithms better that we can then fly in the future on a mission to go service a satellite. So those were the experiments we did actually up in orbit. And then Tammy's kind of leading up, one of the many jobs she does is all the tech transfer to industry. People that want to license the work we've done, experience we have, can approach us, and we can set up different agreements with different companies to do that, to get that in industry. We have, every so often we get together and talk about the work we're doing in the government. Cosmic's now trying to organize that a little bit, kind of across the government, academia, and industry. And then obviously we do things like this, like making sure we have the next generation workforce, giving you all challenges in schools you can come work for someday. And then tons of outreach. Colleen's, one of her many jobs is to go out and talk to the public about all the cool stuff we do, tons of events. Next slide. And so you saw the rock, and you went through the rock today, is that right? So it's one of the many facilities we have. You saw the motion platforms we have in there to simulate different portions of space flight. We have another building just up the street here. It's called the Service and Technology Centers, where we do all the work we do on space station. So we basically have a robot that's used by car companies to weld cars and paint cars. And what we do is we put an end effector at the end that's just like the end effector on the space station robot. You can have that robot simulate as it's in space, doing what it needs to do. And that's how we get a good representation of what the tool needs to look like. You see the tools, the font colors and the And all these marks and stuff was all stuff we developed here, because we shut the lights out and we'll do a task, and I can't tell when things inserted. All right, add a yellow band, and so that's how we work all that out on the robot. We get very specific down to the nuts and bolts, simulating work there. And then we have a partnership with Western Virginia University in Morgantown. We have a facility in Fairmont. We have a large piece of granite where we can simulate things floating across flat floors when you want to do that fine contact dynamic motion that you really can't do on this robot you saw on the rock. A little too big to have it simulate a satellite floating through space. So this granite table allows you to get really fine precision and tune your algorithms and work out all your logistics of how you're going to grapple maybe small satellites and that sort of stuff. So I think probably some universities should probably have smaller granite tables. This one's 15 by 19 feet. It's a huge, big piece of rocks. Thanks. And so a lot of the work we do kind of here at Goddard, right? ISAM's a lot of things, right? The work you're all doing, encompasses tons of different areas, let alone within assembly, servicing, manufacturing. But here at Goddard, kind of things we focus on. You saw some of the robotic work we do. Our engineering arm, for OSAM 1 was back in the back of the rock you saw there. We partner with our friends at Kennedy Space Center, who are the world's experts in putting fuel in satellites on launch pads. We've had them work how do you put fuel in a satellite in orbit, which is challenging, right? You have pressure bladders you need to go against and cut wires and get into it. So we have some experts down there, let alone facilities where we can actually transfer really nasty propellant, right? Some of the stuff we put in these satellites, you couldn't do in a room like this or even the rock, because that stuff, one whiff of it, you've got a really, really bad day. So Kennedy has some facilities down in Florida. We work with them. We spent a lot of time trying to develop what we call cooperative servicing aids, right? It's really challenging to go service satellites because they're not really meant to be serviced, right? It's not easy to get to things. And so no one's making them easy to get to because no one's servicing satellites. It's kind of chicken and the egg. So we're trying to show there are ways you can make your satellite more serviceable. Some are free, like take a picture before you launch it so you know what's behind the blanket. Sometimes we don't know what's behind that blanket because the company doesn't exist anymore that built it. All the way up to adding really fancy graphic fixtures and things like that. So we're trying to show the range of possibilities you can put on a satellite to make it easy to service in the future, so then the industry is more likely to go do that. So we spent a lot of time working on that. A lot of work on the ground, with testing of things both on orbit and the ground like you saw on the rock, and rendezvous and processing operations. We have a group at Goddard that typically does guidance network to control satellites, and so this is RPO, rendezvous with the satellites, kind of a more specific version of GNC work that we do all the time here at Goddard. So that's one of the areas we focus on. And you can see what kind of, again, OSAM, ISAM means to people, tons of different things. Some of you mentioned before, replacing things, repairing things, replenishing things, servicing things, assembling, inspecting right before you even go in and know what you need to do. You need to go fly by to see what happens. We've had satellites where we're not sure why the battery, did the battery blow up? What's the side of the spacecraft missing, right? So just knowing what happened will allow you to go back and fix it. And then where we're headed is to be able to really, here at Goddard, as we said earlier, Goddard's a science center, right? All the engineers at Goddard, we work to support the scientists to build telescopes and things that collect data in space. So if you really want to, get really cool pictures of galaxies and solar systems and that, you need really, really, really large telescopes. So that's where we're kind of headed to get that all working. So, yeah. I think I might get in there.
Yeah, that was the
Yeah,
end.
here you go. Any questions?
So where does Aerospace Corporation fit into all this?
So Aerospace Corp manages, or I guess they.
Yeah, they facilitate Cosmic on behalf of the federal government. Now, because NASA is leading the way with ISAM, we play a big role in being contract monitors and giving direction to Aerospace Corp. I don't know if your question was specific to Cosmic and this event here today, but our relationship with Aerospace Corp is a close one to kick off Cosmic. But as other government agencies see the merit in ISAM, nobody needs to tell the Space Force they already know they're doubling down on what they want out of ISAM. But as other government agencies like NOAA and USGS and NRO look at the merit of it, then we expect them to have a bigger role in presence in the cosmic community.
The government as a whole, Aerospace Corp has a lot of expertise they provide to the government. Mostly the DoD, we do a little bit of NASA, but they'll do like independent cost assessments for us on occasion and provide expertise across the government. So If you want to maybe say some more.
Okay, I work at H.A.D.E.S. I'm with Cosmic. I lead the administration infrastructure for this area. So aerospace is a trusted entity to the government. We're a federally funded research and development center. So we are a trusted partner to the government. So we have been contracted to manage Cosmic entity. Cosmic is nationally funded through NASA. We are funded from NASA to manage the entity, but Cosmic is its own independent,
And, when I started at Goddard, I was a contractor. There's contractors that work on center. They're sometimes treated as a government employee versus contract, like Lockheed. We contract with Lockheed people outside that sit outside the gate. Those contractors are treated a little differently. As she said, right, Aerospace Corp is kind of a trusted partner in that there are times when they don't really represent the government, but they can be trusted as if they're a government employee. Like the government employees only people who commit the government to do something. The contractor can't say, I'm gonna build a space shuttle tomorrow. Right, the government has to say that, and so Aerospace Corp has a role where they can kind of be a quasi-government employee in some cases. It's like an expert for DARPA or for NASA.
In terms of the eyesight technology capabilities, which of them do you think is like closest to maturity and like regular use, and what is like the most unrealistic part of that?
Good question. I think rendezvous sensors are ready to go. We do that all the time on station. I think robots are there and ready to go. We just need the will to go do it. I think fill and drain valves, like cooperative valves, are easy to refuel rather than cutting wires and tape, like you see on the length of the thing over there. Those are ready to go. The stuff that's further out is probably some of like the cryo transfer, right? Because storing cryo temperature is really challenging. Instrument swap out, we've done in Hubble, but things like for Roman and how worlds need some fine, delicate way you're latching things in, that's a challenge we're still working on. It's really a will. Someone needs to go, we just need to go do it, right? That's why we're trying to get this started. And I think the more the government demonstrates it, then more companies are going to go do it. It's kind of been, companies have been reluctant because no one's really gone out. So I think those are probably more the
Okay.
far challenges.
I hate to cut it short, but we will have time to talk about all these questions during lunch and breaks, and there are going to be more NASA people here during breaks and lunch and stuff, so you can have all of this conversation then. But we do have to get started, and I think that Osiris is first. So if you guys want to get on up there, we can get started.
And for slide changing, present single view.
Actually, it's going to be online. There, it's already up there. Let me put it full screen. For slide changing, can he just verbally say that he wants the next slide? Jacob?
Yeah,
Or
yeah.
Rachel?
Just give it a next. Rachel will advance it.
All right, great. So just say you're ready for the next slide and they'll change it for you. There you go.
Okay, I'm Jack with Osiris, and I'll be giving you a quick overview of our mission. Next slide. So we've made Project H.A.D.E.S that stands for Autonomous Tethered Extension Fixture, and we're targeting the capability gap that outlined by the decommissioning of the space shuttle, where there is no economical way to service objects in low orbit anymore. Specifically, we are going to develop a payload capable of refreshing or supplementing a target's GNC system by the creation and development of a near universal docking claw. In order to do this, we'll have to achieve 4 key operations, with that being rendezvous with the target, dock with the target, communicate with the ground, and then supplementing the target's GNC system. Next slide. So here's a quick view of our team. We have me, Jack. We then have Aziz, Tyler C, Tyler B, Dev, Photios, and Logan. Next slide. So some major system engineering milestones you can see here. Overall, we had a pretty in-depth development process. And some important things to note is we identified our target. We then developed 3 key ideas to solve the problem. We then developed things such as the system requirements, mission requirements, and stuff like that, as well as system architectures, before moving on to picking the best option. Gotcha. Sorry, is that better?
Yeah, that's great.
Gotcha. Okay. And then we went on to breaking up the mission into a couple of subsystems that we each had to specialize and analyze and trace studies for. Next slide, please. So the impact of H.A.D.E.S. Well, for one, it's going to allow for the mission extension services for objects in LEO. It's going to allow for orbit-tending missions, for gain-of-function missions, and potentially space-run harvesting, and overall make ISAM a much more economical place. Next slide, please. So some similar missions is the Northrop Grumman's Mission Extension Vehicle. This is a vehicle that's currently in operation and services satellites in geo orbit. It is successful right now and is servicing a $3.2 billion market and is an extremely capable vehicle. However, its very large size limits its economical options of potential targets to high-value targets in geo orbit. Additionally, it requires a liquid apogee engine in order to dock with its target satellite, which restricts its potential targets further. Next slide, please. So in order to overcome some of these restrictions that the MEV has, we came up with three main ideas. One, using smart memory alloys to have a night null actuated docking method, a linear actuated docking method, and potentially using cold welding as a way to perform docking. Next slide, please. However, upon the completion of a concept down select decision matrix, we ultimately went with a night null actuated docking method due to its simplicity and large design reserve it afforded us. Next slide, please. So how is H.A.D.E.S different than MEV? For one, we use night null and gecko grippers in order to dock as opposed to the liquid apogee docking engine, which requires no onboard hardware with a target satellite, expanding the potential targets greatly. Additionally, H.A.D.E.S is significantly smaller than the MEV, being around 15 times lighter, uses 22.5 times less power, and is about 1/25 the volume of the MEV, allowing for a much more economical launch, vastly expanding potential targets that makes economic sense to provide its mission extending services. Next slide, please. So why night null and gecko grippers? Please go to the next slide. There's a video on this slide. So night null has no moving parts, and you can have it set to an initial cast state, then deform from that state, and then have it basically go back to the initial set state by applying a heat to it. It reaches a certain activation temperature, and then it reforms to its initial set state. Benefits of this is it's extremely easy to mold into its set state, only requiring it to be heated up to about 300 degrees Fahrenheit, allowing it to be customized economically for each target satellite without major system overhauls. However, one problem identified with gecko grippers, night null, was that there was a potential of it sliding between the payload and the target satellite. In order to remedy this, we use gecko grippers in order to lock the target in place, which we use gecko grippers because they work in a vacuum, require no active power requirements, can be cycled many thousand times, and have upwards of 40,000 kPa of sticking force. Next slide, please. So in order to further develop this idea, we made a prototype in order to demonstrate the docking methods we could use. Please play the first video. So this is a more gecko gripper dominated docking method where the gecko grippers provide both the anti-slide lock-in effect and the sticking force for the docking method. This allows us to stick to essentially flat surfaces. However, it has the downside of being much weaker than the night null dominated docking method. Please play the next video. This video shows the night null dominated docking method where most of the load is channeled to night null, giving much more strength, whereas the gecko grippers in this mode mostly are there to prevent any sliding. Next slide, please. Now, in order to do some system development and mission integration and mission planning, we had to pick a target. And for our target, we decided to pick Hubble. There's a couple of main reasons for this. One, Hubble's GNC system is failing right now with its gyros nearing its end of life. NASA also publishes information on Hubble much more freely than most companies do, making our jobs easier. Additionally, Hubble is in LEO and has services that would allow us to test both of our primary docking methods. And then finally, NASA has already shown interest in potentially sending a mission to help deorbit Hubble or extend its mission life. So at the very least, they should be able to hear us out. However, If NASA says no, no worries. We have enough mass and volume excess or reserve in our design to send up a microsat to use as our test bed in case NASA says no. Next slide. So here's a storyboard of our complete mission operations. We're going to launch into a parking orbit below Hubble. From here, we're going to separate from other ride-shared satellites, then establish a link with the ground, conduct a systems test to ensure everything's working properly, then wait for a transfer window to go up to our targeted orbit with Hubble, rendezvous with Hubble, dock with Hubble, verify the integrity of the dock, perform a small systems test to ensure everything's working as expected, and then move on to something Hubble to its new end of life. Then we could either help re-enter with Hubble aiding its deorbiting, or NASA's only deorbit Hubble. Our payload is also fully capable of deorbiting on its own. An important thing to note about this diagram is that the tasks outlined in blue are semi-autonomous tasks, while our tasks outlined in yellow are fully autonomous tasks. What we mean by semi-autonomous are tasks the payload can complete fully autonomously. However, it requires human authorization in order to start that task, in order to minimize any risk posed to our target Hubble. Then, next slide, please. Moving on to a more payload-specific mission overview, we're going to use GPS transponders in order to close about 200 kilometers of Hubble, or then we're going to switch on our visual systems. Use that to close about 200 meters, or then we're going to turn on our LiDAR system. Then using both LiDAR and the visual system, we're going to close about 10 meters. At this point, we're going to maneuver to our designated dock point, confirm everything looks good, then continue to close the distance further. Then we're going to stop again once we're much closer to the target. From here, we're then going to once again confirm everything looks good before then closing to 1 centimeter. At this point, we're then going to deploy the night null in order to bring us that last 1 centimeter, and then once the night null is fully deployed, we're going to use the gecko rippers to lock us in place. After this, we're going to conduct a visual system check to make sure everything looks good before conducting our small test maneuver. Once again, blue tasks are semi-autonomous, yellow tasks fully autonomous, with semi-autonomous tasks being capable of being fully autonomous, requiring human authorization. Next slide, please. So here's an animation of our dock procedure. So here you can see us closing to the target. And right here, we have the night null being actuated by us applying the power to it. It is currently closing on the targeted member. Then once it's fully deployed, GatorChomp will be activated here, and then visual detection will occur before conducting the small test maneuver. And all of this will happen over the span of a couple of hours. Then, next slide, please. So here's a detailed view of our payload. The most important thing to take away from this is that we are well under volume constraints, only using about 50% of the allocated volume. So important parts to pay attention to is the docking clamp, LiDAR, and camera systems. However, most of the other key components moved into the bus in order to better protect it from radiation, and that is the main limiter of our mission's life. Next slide, please. Here is a more detailed view of our docking claw. And you can see here, this is a side view of what each band will look like, including the thermal insulation. And then we have docking and undocking bands to allow us to attempt multiple dock attempts if required. Next slide, please. In order to select our materials for this docking band, we conducted multiple trade studies in order to best pick the best material for the job. Ultimately, Kevlar was chosen due to its high operational temperature, insulating properties. However, we identified that Kevlar is weak to UV rays, so an additional material was required to protect the Kevlar from UV rays, which was ultimately decided to be an MLI that will also provide further thermal insulation. Next slide, please. So we then conducted some structural analysis to ensure that our payload could survive launch and max operational conditions. Overall, we conducted FEA for launch conditions and operational conditions and found that with our current design, it holds up very well. Next slide, please. So then we conducted some thermal and electrical analysis to ensure that the night null clamps wouldn't heat up too much or require too much power. What we found is that the longer we take to activate the night null, the more favorable the power, thermal, and amperage requirements are, overall becoming very manageable past about 90 seconds. Next slide, please. So we then did some selection of our GNC system and thrusters. Overall, we just made sure we had a system capable enough to ensure that we could service most satellites in LEO, if not all satellites in LEO. Next slide, please. Then for the actual bus and payload for that matter, we conducted some thermal analysis to determine whether or not we would need more active thermal management solution to this radiator. And upon this thermal analysis, we did determine that in the worst case scenario where everything is firing in full sun for a full orbit, there were potential cases where we would have a bit excess heat generated. So we did include a radiator, although this will not be used for most of the mission. Next slide, please. We then moved on to conducting orbital analysis and then the selection of a propulsion drive in order to make sure we can meet our delta V requirements. And then we conducted a very loose volume verification to ensure that all of our parts, while factoring in a certain factor of safety to ensure that we can account for plumbing, structural elements, stuff like that, would fit within our specified payload, bus size. Next slide, please. So here we have a data flow structure for our payload sensors to our bus. And we took this from a NASA project that was developed in conjunction with Blue Canyon Technologies. And the reason we use this is that it had a very similar function and sensors that our payload will use. Next slide, please. So then moving on to comms, we decided to go with 2 ground stations, one in South Point Station, Hawaii, and one in Santiago Station, Chile. The reason for this is that during the actual dock phase, we would like to have an active link with our satellite for as long as possible, so that way we can provide the human verification and potential abort commands if absolutely needed. Aside from that, after the docking sequence, the active uplink is not required. You can upload maneuvers to our payload and execute on a designated time. And also, an operator will be the same as operator's Hubble after the docking sequence. Some other information is that our downlink margin is going to be about 3.1 decibels. Our uplink margin is going to be about 2.8 decibels with a rough data bit rate of about 100 kilobits per second. Next slide, please.
Can you hold the mic a little bit closer?
Yeah,
They're having a hard time reading or hearing you online.
Sorry. And then upon completing all of this analysis, we then can make sure that we fit within the mass constraints and power constraints of our mission. And we found that we fell well within these constraints. We were allocated 70 kilograms in order for our payload, and we're only currently using around 18 kilograms. Furthermore, our team went with the 444 watts power supply option, and right now our payload is only using around 215 watts. Next slide, please. Now, when it comes to risk mitigation was a very important feature throughout our entire payload development phase, and influencing many aspects of our design. The first one we identified was the risk of a premature or uncontrolled docking instance due to solar heating. The reason for this concern is that nitinol only cares about reaching a certain critical temperature, and after it reaches temperature, whether we want it or not, it is going to begin performing to that set state. In order to mitigate this, we did 2 things. One, we provided thermal insulation from the sun and the nitinol bands as a Kevlar and MLI layers seen earlier. We then also just built into the mission plan times in which we're going to orientate our payload away from the sun whenever possible to ensure it gets as little solar exposure as possible until we begin the dock procedure. The next risk we identified was surrounding a failed dock attempt. Initially, we had no way to undock from the target, which would mean a single failed dock attempt could spell disaster. In order to mitigate this, we incorporated both docking and undocking bands, where we're going to have the docking bands be set around a certain target on the payload and have the undocking bands be set to be flush with the top of our payload bed. So then all you got to do is activate the docking bands and it will bend towards the dock state. If you want to abort it, all you got to do is apply power to the undocking bands, and that will then bend the docking bands away from the dock point, allowing for potentially unlimited dock attempts, with the one downside being there needs to be a certain amount of cooldown between the dock attempts in order to let the bands cool down. The next major risk identified was the risk posed by our target and payload colliding during rendezvous and dock. In order to mitigate this, we did 2 main things. One, the thrusters we selected are primarily cold gas thrusters. However, if required, they can become hot gas thrusters, vastly increasing their thrust size, allowing us to quickly thrust away from our target if required. Furthermore, we also are incorporating multiple sensors in order to ensure that we have high quality position data at all times during the dock procedure, even if the sun's shining or we're in complete darkness. The next big risk identified was the risk posed by our docking clamps failing to fully arrest ourselves between the payload of the target, causing some sliding, which would be very bad for a GNC system, as we would not know where we're pointing exactly. As I said before, in order to mitigate this, we incorporated gecko rivers in order to ensure that no sliding occurs, as in order to cause sliding with gecko rivers, it require a thrust of about 200 newtons, which is much, much greater, about 20 times greater than the max expected operational load. Furthermore, and then the last major risk identified was the risk posed by our target blocking the sun from our solar panels. This is a very likely eventuality, as we have to dock at the best location, which will most likely not be where the sun shines the most. And as such, in order to mitigate this risk, we developed a very large design surplus into our power budget, so that way, even if the target blocks about half of the sun coming onto our solar panels, we can still operate with full capabilities. Next slide, please. So some technology that will really benefit HF is one, advancements in thermal systems. Nitinol can be cast and recast to multiple set positions by just heating it up and then quenching it, meaning that if you can get advanced thermal systems allow us to heat up the nitinol about 300 degrees and then cool it down, we can allow it to be set and cast to multiple different targets without having to launch a new payload. Another advancement that would be very nice is advancements in lightweight and compact radiation shielding methods, as right now one of the main limiters on our mission life is radiation exposure and damage to our electronics, allowing for each individual HF payload to operate much longer. The next technology gap that would really help us if it's filled is advancements in on-orbit refueling, as on-orbit, as it will allow us to refuel the limited reserves of both thruster and propulsion fuel without having to launch an entirely new payload into orbit again. Ultimately, all these technologies allow us to drastically cut down the cost of HF even further. Next slide, please. So some of the biggest challenges we encountered was how to insulate the nitinol bands. The reason for this is we have to both insulate it from the sun and from the docking and undocking system from each other, because if the docking system heats up the undocking system to its critical temperature, nothing will happen, as the docking system will pull towards the dock point as hard as the undocking system will pull away from the payload, the dock point. Now, in order to mitigate this, it's a pretty hard challenge. We have to find flexible insulators, although we found a pretty interesting source of flexible insulators in space materials. The next big challenge we encountered was finding detailed information on certain parts or like components for the spacecraft development phase, as there were certain times we really wanted a specific, like either size, volume, weight, or cost of a part, and that just simply wasn't given to the public. So we had to either go through, email the company, see if they'd be okay with letting us find out about it, or even at some points do some pixel counting and mass estimates. But ultimately, we were able to, with significant time investment, overcome these challenges. And then the final major challenge we faced was breaking up the design of HF from one monumental, seemingly impossible challenge into many multiple, much smaller, bite-sized challenges we can mark off one at a time. And that was a pretty big but pretty important challenge. Next slide, please. Some lessons learned. We learned that sometimes a simple, quick physical model can really help you in the design of a complex system. What you see there is a one-to-one scale model of our bus and payload, and it allowed us to really come up with certain design considerations we failed to consider without that model, such as how the solar panel might not be able to fully make use of its rotation because of the designated dock point, and also really aided in us coming up with the placement of certain subsystems and parts. The next thing we came up with was measure twice, cut once, or what I mean by that is be very careful with the steps and decisions you make early on in the design process, as if you make a mistake there, it becomes exponentially harder to fix that mistake the later on you realize it. And then the final major thing we learned was that spending time to learn the proper CAD tool before conducting any analysis will save you time in the long run. Even if initially you're kind of just twiddling your thumbs watching tutorials, it will save you time. Next slide, please. So, how quickly could an H.A.D.E.S model be produced? Well, we think fairly quickly. This is because whenever possible, we use off-the-shelf components and parts, or if those are not able to fit our needs, we use stock materials that can be cut down to size and given to be in with very basic manufacturing techniques such as CNC machines and laser cutters. Additionally, the only part that would require completely base up design and testing and verification would be the docking clamp. However, the docking clamp could be made for a roughly estimated cost of below 20K in raw material cost. Next slide, please. So here's a rough bill of materials. As you can see here, we have most of our parts selected. And when looking at the off-the-shelf component, you can see that most of them are actually off-the-shelf. Although it is important to know that the parts that are not off-the-shelf are parts that their stock material can be bought straight off of a supplier and then cut down to size using those basic manufacturing techniques such as CNC and laser cutting. Next slide, please. Here's some basic information about the paper we submitted. 213 word abstract, 18 pages, and a 7,000 word count. And it's going to be submitted to the AIAA Science SciTech Conference. Next slide, please. So as we're past the PDR, we're going to plan on basically updating the design and optimizing it. Right now we have a design that works. However, there are several steps we need to do in order to save some weight here and there. Additionally, we're just going to mostly focus on the actual integration and construction of a real-world demonstrator, as right now most of our designs are generative design placements. And ultimately, we're also going to make sure that NASA is okay with us using Hubble as a target, as if it doesn't, we need to get on top of that now. Then we're just going to move on to the integration steps of the spacecraft, and then actually looking to essentially sourcing the components we need in order to make a real-world demonstrator for the docking clamp. Next slide, please. So in summary, H.A.D.E.S will enable economical missions, extension services to LEO, orbit tuning missions, gain-of-function missions, space junk harvesting, the expansion of ISM capabilities, and the satiation of an existing $3.2 billion market. H.A.D.E.S, when compared to the MEV, is 15 times lighter, 22.5 times less power hungry, 1/25th the volume, and much easier to launch. All of this is due to the fact that H.A.D.E.S utilizes a nitinol and Goddard actuated docking clamp, off-the-shelf components, basic manufacturing techniques to manufacture, and minimal novel technology to be proved. And with that, any questions?
All right, let's open it up to the judges for questions. If you're asking questions in the room, they'll need a mic, or you'll have to repeat the question.
What is that?
I have one. This is Russ Snyder from NASA. Are there any restrictions on the interface on satellites that the gripper devices are going to interface to? Like, what specifically are you planning to grab on satellites, or can you grab?
So we can grab onto any flat surface or like a protruding member. The main constraints with like the grip onto a flat surface, or it can even be a curved surface. It can be like an open surface, and it can be customized to fit a relatively small surface. The main restriction with that would be, depending on the surface, it's like purely MLI or like a strut, it would affect the maximum like thrust or change in like momentum we could apply to it without potentially carrying the MLI or things like that. As for like the protruding band or like protruding fixture, we would be looking at like either service handles on Hubble that we looked at, or like a potential like comms boom. And once again, we have to, you can customize it to fit any like shape or size relatively easily. And once again, the exact like loading requirements will be limited by that piece we attached to.
All right, we got a question in the room.
Could you go back to the gripper cycle life slide?
Yes. Could you go back to the slide that's talking about the nitinol, the animated nitinol activation? I think I did. Could you go back to the slide involving like the animation of nitinol working? The one before this, I believe. Oh, yeah, this one?
So are you saying that the cycle life of the nitinol is 30,000 cycles, or because I think probably much higher?
Oh, yeah, sorry. No, this is for deco grippers, like the sticking material where you just lock things in. It was cycled to 30,000 times without any significant degradation in it. Nitinol can be cycled many thousand times. There's like no real limitation in how many times you could cycle it. There is going to be like some degradation over like hundreds of thousands of cycles, but not practically speaking. They can be cycled as many times as needed.
Right. So I was wondering if there's any sort of thought into how you monitor performance of nitinol in terms of how it grips and how it gets.
Yes, we did consider this, and we are potentially looking into adding a fixture on. We could like extend from our payload, have nitinol grip around it, and then apply a load to that fixture, because we can just measure how much force it takes to form the nitinol. Because if nitinol is deformed, no big deal. We can just apply the power to it again, and it will return to its set state. So we can basically have a designated like force applicator from the bus, and have that deform the nitinol to estimate its performance.
I think we have time for maybe one more very quick question. Otherwise, I think we can thank our speakers, Team Osiris, and we'll take.
Do you have any other team members here?
Yes.
Okay, go up by the screen, and or at least by the over here, and I'll take a picture of all you together. Well, yeah, I know, that's what I was just thinking. Yes. I'll want to go to the back. 1, 2, 3. All right. You guys look at me. One more. Nice. Good job, guys. Thank you. Okay, now we have Starforge from Ohio State. Jacob, is it better if we use the mic or if I just speak like this?
I need the 1-2 comparison.
Like, you leave the phone at the phone. Yeah, we just give them on the phone and mute that laptop and have the phone unmuted.
That would probably make it way worse.
That's what I was gonna use. You would arrow real bad and make the.
Yeah, that would be enough. No, this will work fine. It's because this is picking up the audio, so it's fine. I turned down the mic, so it should be better now.
Jacob said it sounded better.
Yeah, I think it was too loud. I'll turn it over.
Testing.
Yeah, okay.
Okay, is that good?
Yeah, I think so.
Perfect. Okay. Go ahead and get started. Okay, hello everyone. My name is Chip Orban. I'm here with Team Starforge from The Ohio State University. And today I'm going to be taking you through our submission to the C3 challenge. Next slide. Here is a quick team overview. In total, we had 12 team members, all with diverse skill sets and fields of study. As for myself, I'm a third-year industrial design student who's minoring in engineering sciences.
Hello, I'm Dustin. I'm a graduating aerospace engineering student at OSU as well.
I'm Janesh. I'm a graduating ECE major, which is electrical and computer engineering.
My name is Shreya Sundurkar. I'm also graduating senior in electrical and computer engineering.
Next slide. Next slide, please. Okay, Okay, so our team was interested in the issue of small space debris, specifically how ISAM can be integrated into existing technologies to actually mitigate space debris. And so basically our team is proposing a satellite concept that does three things. It detects, it tracks, and actually eliminates space debris smaller than 10 centimeters. And so with our submission, our team wrote a technical paper that summarized all of our research and development, as well as we created a small prototype, which is seen in the front of the room here, that is going to showcase our three main operations. Next slide. And so space debris is going to, there we go. That's it.
So our timeline reflects a deliberate approach to project development, with each milestone building momentum towards our goals. So we kick things off on September 6, 2024 by appointing a project manager, establishing leadership, structured communication, and solid decision-making process from the start. By October 12th, we had fully initialized operations. This included setting up our development environment, assigning roles, and finalizing our tools and workflows, laying the groundwork for collaboration and execution. On November 10th, we reached a major milestone, defining our system requirements. And through stakeholder interviews, technical analysis, we created a clear foundation for design and engineering decisions. Our January 13 milestone marked the completion of trade studies comparing technologies, design paths, and costs, which directly informed our conceptual design launched on March 3rd. At this stage, we built mock-ups and blueprints that align with the system goals. Finally, on April 1st, we established a roadmap to our preliminary design review, defining success criteria, identifying risks, and outlining the next set of deliverables. Next slide, please.
Okay, so small space debris is going to impact several areas of the space industry, notably just general scientific discovery, as well as climate research for Earth, and even defense initiatives, and ultimately the expansion of a space economy. And so the picture on the right here is of the Canada arm of the ISS, and it's showing some space debris damage there. It's just one example of the kind of risk that space debris poses in space. And so to give you a bigger scale of the issue of space debris, as of May 2024, there are about 99,000 active satellites orbiting Earth, with an estimated 670,000 debris pieces that are smaller than 10 centimeters. Next slide.
So we approached feasibility from like two different angles here. We did both a conceptual model and a prototype model for our feasibility. The conceptual model kind of focused mostly on a fully functional product being assumed, and we were just looking at analogous components, choosing those, and then integrating them into the Venus bus system. So all of those features are market ready according to our concept model. Estimated cost of components in total was about $102,000, not including the bus itself. So that's additional parts that would go into it. The prototype model was more for testing our methodology, making sure detection is possible with the current systems that we had planned, and then doing other validation steps. So that was estimated to be about $200 for the prototype, and actually it's that exact one sitting there was what we built with that. So yeah, next slide, please. Cool, and this is kind of our systems flow chart for our prototype itself, what we're doing that's special. So once we launch, the satellite will go around orbiting Earth and detect debris along its orbit path, determine whether it's larger or smaller than that 10 centimeters. If it's larger, it just kind of logs it. Ground stations do that already. It's just there for good backup data and to test or to validate our results there. If it's smaller than 10 centimeters, that's our main focus for our mission here. We're going to do that same logging step, but then we also are going to continue to propagate that orbit in time, and then aim our laser at it, and then fire this laser at it to either ablate it or give it just enough momentum change to deorbit it faster than it would already doing. And then update that log, make sure that this debris is either properly mitigated, or if future action will be needed. Ideally, it's mitigated in one clean foul swoop to reduce the risk of additional issues by changing its orbit to a potentially more dangerous one. And then it'll take that, send all that data to ground stations for further analysis, to update our models and perform better operations over time. After the mission is over, our spacecraft would either deorbit if it's a candidate. It might be too large. If it's too large or certain materials won't burn up properly, it would just be moved to a graveyard orbit and be dealt with later. Next slide, please. So when it comes to the required elements, we had about 4 functions working together, or 4 user needs. So the first one was autonomous operations with an importance of high. The existing solution is limited autonomous ISAM systems because the current systems are still experimental. So we need to fix that. The second user need is in-orbit servicing capabilities. This is also of high importance, but we have manual and ground-based servicing currently, but there are high costs and time delays. After that, we have modular design for scalability. This is of medium importance because we have limited modular designs, but we also have them, but we have lack of flexible systems. And finally, we have minimal remote commands. The importance of this is currently high because we have remote controlled systems, but we need a lot of frequent human intervention. Next slide, please. So when it comes to our trade studies, we divided our teams into 3. Our first sub-team was 4 members focusing on coding, testing, and data analysis. Our second sub-team was focusing on CAD design and prototyping. And finally, our third sub-team was also focusing on planning, documenting, and communications. All of them had 4 members. Next slide, please. So when it comes to our risks, we have highlighted our critical risks with the direct stakeholders involved, but also the design steps that were needed. So the first critical risk was scheduling on a large team. The direct stakeholders were team members and advisors. However, the likelihood of occurrence was about a 95%, meaning this was bound to happen. But the scaled consequence of this scenario was about a 3 or a low. After this, we had communicating assignment status. The stakeholders were the sub-teams and the NDC team, with a likelihood occurrence of about 50%, or medium, but the scaled consequence was a 6 out of 10. Finally, the biggest one was budget allocation. We had the sponsors and MDC team involved as the direct stakeholders. The likelihood of occurrence was about 10%. However, the scaled consequence was about a 9 out of 10, meaning it was very high. The project would not go forward without a budget allocated. After that, we had prototyping quality with a large amount of stakeholders, including sub-teams, MDC team, lab and shop managers, with a likelihood of 30% or low. The scaled consequence was also a 6 out of 10 or a medium. And finally, we had defining user needs with team members, sponsors, and end users as direct stakeholders, and the likelihood of 70% or a high with a scaled consequence of 8, meaning this was also very high. So when it comes to the mitigation strategies we used, we involved regular communication, assigning leads within sub-teams, planning budget advisory meetings, and researching similar projects, setting realistic budget and time goals, and also finally keeping in touch with sponsors and reviewing user needs. Next slide, please.
Okay, so walking you through the story of our satellite concept, everything begins with a launch into low Earth orbit, followed by the deployment of the Venus-class bus into space. Followed by this is going to be a LiDAR debris scan that's going to give information about speed and direction of different debris that's encountered in space. That's going to tell the laser head inside of the satellite payload how to actually align itself and point in the direction of the debris path, which leads to step 5, which is on the next orbit around Earth. The satellite is then going to fire its laser at the direction of the debris path and effectively mitigate it, or at least push it into the atmosphere to burn up and dissolve. Finally, at the end of the satellite's lifespan, we're imagining a kind of shuttle technology to actually collect and deorbit the satellite, or perhaps multiple satellites. Alternatively, the satellite could jettison itself into Earth's atmosphere and burn up that way. Next slide, please. Here is a quick video. Should go straight to YouTube here. the embed link in the presentation. It's
If you have a team member online, oh, that's a PDF. Do we have the PowerPoint of their briefing? Or if one of your teammates has it, they can speak up and we can make them a host temporarily.
Yeah, we have a video on one of our laptops.
Or do you know the link? You can also just tell me the link. Private link?
It's a listed link.
Okay.
Why don't you describe what the animation is showing?
Yes.
Which I know is not what we want
I
to
think
do,
that's
but
probably the best idea for now, and then
Okay.
if you find it, you can show it.
Right. Sorry about that. Basically, it's just a quick animation of the three primary operations of our concept. So it begins with the LiDAR scan that is sweeping over Earth. And so any debris that passes through the scan is going to give the satellite information on the debris speed and direction. And so that's going to be tracked inside of the satellite computer system as an orbital path. And then that's going to allow the head to then align itself to meet up with that debris on that specified orbital path. And that allows for the laser head to then fire and mitigate the debris itself. Sorry about the video. Next slide.
So in space, when the unexpected happens, real-time communication lets mission teams act quickly, especially in high-risk or time-sensitive scenarios. Now, while the system is designed to operate semi-autonomously, we still see value in human oversight. Constant monitoring isn't required, but having the operator on standby can help validate data, spot anomalies, and offer judgment in edge cases. During normal operations, the system efficiently manages routine tasks like tracking and mitigation, but during critical moments such as system transitions or emergencies, optional operator involvement adds an extra layer of safety and confidence. Lastly, let's touch on the data bitrate. To support high-resolution tracking and frequent updates, the system is built to scale. Once data loads approach 500 to 1,000 gigabytes, the communication protocol adapts, shifting transfer intervals to prevent bandwidth congestion and ensure priority every data is sent first. So it's important to continuously monitor the volume of data being collected and adjust the transmission strategy accordingly. Next slide, please. Let's start with one of the most forward-thinking ideas we had, which was equipping our spacecraft with onboard LiDAR. Now, traditional ground-based tracking has its advantages and its limitations because it's affected by weather, line of sight, and can't always respond quickly. But with LiDAR on the vessel itself, we gain real-time 360-degree awareness in the orbit. It also allows us to measure not just the position and the speed, but also the direction of travel, orbits, object size, and even hints at the material composition, which is a huge leap in situational awareness. Building on that, we looked into using laser systems to actively deal with debris. For small to medium-sized objects, we'd use focused laser pulses to nudge them into a lower orbit where they'd safely burn up in the atmosphere. But for the really tiny fragments, the kind that are too small to track but are still dangerous, we aim to vaporize them in the orbit. That's faster and it doesn't require as much data beforehand. Now, of course, a system like this needs to have a smart way to get enough power to be able to fire up the laser when needed. So we explored solar pumped lasers which absorb and store energy from the sun and then release it in short bursts when needed. This means that we don't have to rely on large, heavy batteries, making the system lightweight, efficient, and self-sustaining over long missions. In the big picture, we're proposing a semi-autonomous, space-based solution for debris management. It can track, analyze, and even eliminate debris without relying heavily on Earth-based infrastructure. And while it's largely autonomous, it still allows for human oversight when needed. This approach not only boosts safety in the orbit, but also helps pave the way for more sustainable operations in space. Next slide, please. So we identified 3 technology gaps during our development stage. One of the biggest challenges in space debris management is detection. Current sensors often fail to accurately identify small or fast-moving debris, and that limits our ability to track threats before they become dangerous. Powering high-performance systems like lasers in the orbit isn't easy. And since solar energy is limited and battery capacity comes with constraints, it's necessary to ensure consistent, reliable power for continuous operations. And lastly, even tiny fragments can cause catastrophic damage, yet no proven small-scale capture system exists. So we need a safe, scalable way to collect or neutralize these micro debris threats. Next slide, please.
So I'm going to take a little bit of time here to talk about the prototype. So most of this prototype was just used to develop the functionality of our testing methods, which I touched on a previous slide already. And results from our testing are used to develop our full-scale prototype, iteratively increase modularity, and then would change out components and stuff like that along the way. But it's going to be a little hard for you guys online to get what I'm saying, but I'll try to explain it a little better too. So you see in the picture on the left there, underneath is where we would house all of the components. That kind of and is analogous to the internal sections of the bus itself, where all of the shielding is at and everything. And then on the top there is the actual effector of the prototype, which would be more on the outside exposed surface. So if you see here, there's two directions of rotation from those two motors, both in the rotational that way, and then rotational on the pitch and yaw. So that gives us a whole range of motion without having to move the whole entire satellite itself. And then both the camera and the laser are moving together here, which is kind of a risk, but it's okay for now. So once it detects that debris, then that laser won't have to do much adjustment to then account for that camera difference. And then it keeps rotating, up, down, cool. Then all of that data is sent through the central processor and then would be sent to the communication system on the bus itself and then sent to ground stations from there. All of the motors are driven from inside and then sent there. The stepper motors would be changed out for a more space-ready component just because stepper motors aren't, from what I can tell, great for space application, but for prototyping, so much easier. But next slide, please.
When it comes to the biggest challenges we encountered throughout the entire year, we have like 3 key obstacles that we kind of tried to address. The first one was cost versus sensor quality. Now, we realized very early on, and this is probably obvious, but high-end LiDAR was very expensive and power-hungry, and we couldn't afford that. So we started to integrate low-cost software and sensors. We deferred LiDAR for later phases. After that, we had a hardware and software integration issue. So we had some calibration issues during data and controlling software integration phase. But we decided to test the components individually before a full system assembly to fix that. And finally, we had space environment design. So we realized that LEO conditions of lower Earth orbit conditions require more robust materials. So we revised our design and added some shielding and upgraded components. Next slide, please.
A couple of next steps for anyone who would to pick up our project after we graduate and leave and everything like that. Refining design is going to be big. There's a lot of integration and studies happen from a prototype into a full conceptual model. Doing a lot of that, that'll take a lot of iterative use case. Testing more of the prototype design, as it scales up, changing out those components for better, higher precision, more expensive components. You'll need to do basically all of the same testing over and over for them. Once you get to a certain scale, you want to start looking more into environmental testing, stuff like neutral buoyancy pools, radiation laboratory, stuff like that, so that you can make sure everything will work in the intended environment without any hiccups that you don't find out until you're already in space. And then lastly, integration with the host bus itself is going to be huge. A lot of cooperation will have to happen between both Blue Canyon, your team itself, and probably some other teams just to make sure that integration doesn't come out with any extra risks there. Mitigate those before we get into space. Additionally, our prototype requires an internet connection right now. Got to solve that somehow. We get all of those files and stuff that it runs off of stored internally. We had the problem of not being able to run it outside of our lab because we don't have internet outside of our lab. But yeah, next please.
This project was truly a multidisciplinary effort, and strong team communication was needed. Not all of the team members were engineers. Our research suggests that in-space mitigation technologies will be essential, especially for addressing debris that's smaller than 10 centimeters, which often goes undetected but still poses serious risks. Innovative, collaborative solutions like ours will be key to making near-Earth space safer and more sustainable. Thank you very much. We're open for questions now. You can go to the next slide.
Okay. Any judges have questions? Yeah. If you're in the room, please ask for the mic. Otherwise, just come off mute and ask away.
Just quickly, I did put the animation link in the chat.
Sarah, you saved us.
Rachel, do you want to click on it since you're already sharing?
Or I can screen share.
Ah.
Jeez.
Just a quick little animation there. That's all we got. Thanks, Sarah, for putting that in there. Appreciate it.
Okay, do the judges have any questions?
Can I ask a couple of questions?
Absolutely, go ahead.
Have you given, the concept actually has similarities with the British Dragonfire, which is kind of very nice to see. Have you given any consideration of how much laser power you would need to deflect certain size debris, assuming it's metal or so on, within the scale that you are targeting below 10 centimeters? And have you also given any thought of how do you want to apply the laser pulse? Is it like a short pulse to give it a deflection, or is it a continuous pulse to give it more continuous interaction with the debris?
Did you hear all of that? Okay.
So we did consider power draw. That was one of the big main considerations we were thinking about for this laser. We did look into using stuff like supercapacitors to give us all of the energy stored so that we can discharge it in more of a quick fashion, and then work on rebuilding that power level over time. So then it would just decrease the amount of basically missions that we could run with that. We also did look at alternative uses other than just like lasers. Like ion beams was thought about. I think proximity was what we ran into challenge-wise there. We'd have to get pretty close for it to be useful. And then solar pumped lasers we kind of looked into, but I don't think we got very far with those, with their theoretical nature still. But yeah, and then like pulse width and everything like that, it would hopefully be a short pulse. Getting accuracy and maintaining accuracy with long pulses would be more challenging. So we're staying on the short pulse side, but that's something that can definitely be looked into in the future to kind of look for something more of a simpler solution than just our original laser idea.
Thank you. And as you envision your demonstration mission, how many debris do you think you would be able to remove? Is it like a handful or a large number? In your best case scenario?
Best case scenario, I would say we're at least doing a couple a month. Over like a 7-year mission, that ends up being a good 90-ish pieces, which, you know, is just like a drop in the pond, but it's got to start somewhere, you know.
Thank you.
Yeah, and a constellation of satellites would increase that too.
Okay, do we have any other questions?
We have one in the room.
Yeah, I was wondering, so the plan is to orbit and face the Earth and just do this sort of sweeping scan towards the Earth, is that right?
Yeah.
So are there any noise considerations, or have you considered it might be better to change the angle? And then also on top of that, you also want to qualify like what the debris is right before you shoot a laser at it. So I was wondering
Some sort of suitability like metrics has to be figured out for that one. Like if we can figure out what material it's made out of beforehand is ideal, but it might not always be possible to determine exactly what material, so we have to find some sort of characteristics that make it a good candidate for ablation versus just like deflection into the atmosphere.
If you're answering, you should hold the microphone so we can hear you.
We did like look at certain characteristics, or like figure out. We're looking for ways to figure out like characteristics for like what kind of metals it could be made of. The reflectivity of it would be an important one to make sure that it's a suitable candidate for ablation. Otherwise, it would just be effective for like deorbit, if even at all possible there. So there would have to be some sort of additional characteristics than just the direction and relative velocity of it. Then there's also that level of uncertainty even with detection in general. Right now, I think ground stations, even for like larger pieces of debris, give it some sort of error cloud to track the debris rather than, oh, it's exactly here in this particular spot. Hopefully, with being closer to it, literally in space, that level of uncertainty can be dropped to a much more manageable level, that using a laser like that would be much more precise and effective.
Okay, and I think that that's going to wrap us up here. So let's thank Starforge again, coming all the way from. You guys should stay up there for the photo, and the judges will take 2 minutes, and like the next presenters are online. Yeah, we'll start at about 9:06, 12:06 for East Coast people.
Thank you.
Thank you.
Okay. Now we have Prometheus.
Correction, it looks like they are in person.
Yeah. It's kind of lower, yeah, but still picks you up. It's good.
Won't we just wait 1 more minute to get started so that the judges can finish typing up their comments? And once we hit 9:06, you can go.
Yeah, it's in the hallway right behind you. Do you want to test out saying something? Is it still on?
Okay. Are we good to go?
I don't
Is the mic on?
know if it's on actually.
Yeah. Just hold the microphone right up to your mouth.
Oh yeah, I know. Oh, okay, now it's on. I turned it off. Sorry.
Okay. All right.
Okay, that's much better. Thank you. Yeah, and you can get started. Thank you.
Perfect. Okay, next slide then. So a problem this team has noticed is the disconnect between methods of servicing, assembly, and manufacturing on Earth and in space. On Earth, a lot of these servicing, assembly, manufacturing jobs are completed with the use of laser cutting and welding, and they're done usually autonomously without personal or manual labor. In space, however, we've only seen welding operations performed manually by astronauts. This is unsustainable, clearly, for future large-scale assembly and servicing missions, and clearly there's a need for popular operations like laser cutting and welding to complete ISM jobs autonomously for future missions. The Prometheus mission is a demonstration of these autonomous welding and laser cutting techniques. The demonstration involves debris from an inoperable satellite to prove servicing capabilities. This mission has 3 objectives to demonstrate this in full. First, Prometheus will rendezvous with a target piece of space debris. Then it will semi-autonomously, with a command, begin a laser cutting sequence, and afterwards begin autonomously welding the debris onto the body to demonstrate these capabilities. So currently the team has concluded a critical concept design review for the Prometheus payload, and has completed significant analysis on the payload integration with the Venus X-class bus, and we're now working towards a preliminary design review. Before we continue, I'd like to mention that currently developed by Think Orbital is a payload with a very similar mission objective to ours, to demonstrate autonomous in-space electron beam welding
We heard about this at the beginning of our semester when our design decisions and mission objectives were already locked in, but we're going to prove to you throughout this presentation that the autonomous in-space welding of our payload is not singular, although it's not singularly innovative, the design of the payload is, and that includes its debris mitigation plans and even the demonstration of the welding that we'll do. Next slide. So to introduce some of my team, I'm going to ask them to wave. Raj is right back there. Then there's Bryce, Dylan, Katie in the back there, led by our team lead, Michael, and unfortunately Joe's out sick. So let's wish him some well wishes. Next slide. So throughout the 8 months that we've been developing the Prometheus payload and this mission, we've hit some really big milestones. First was selecting Raj as our team lead at the beginning of our semester, and then about a month later, we explicitly chose our operations and capabilities as per the RFP, and worked for the remainder of the semester on developing functional architecture, top-level requirements, and doing a concept down select for our system readiness review at the end of last semester in December. In the new semester, we began a deeper analysis of the payload involving numerous trade studies that concluded around mid-February. And from then on, we were able to work to complete a concept design review, and after submitting that for internal review on March 19th, we've been taking a few steps towards our preliminary design review. We can move to the next slide, please. So here we'll talk a little bit. The technical paper provides a greater in-depth discussion of all the highlighted sections listed. We explain the steps taken to complete success for the Prometheus mission, and we total this at about 18 pages, and we're looking to publish this at the SciTech conference. Next page. So I'm now going to walk you through the 5 stages this mission goes through. The first is determining our orbit. This is dependent on the piece of target debris. Some things we considered when deciding debris was if it was isolated, to lower the possibility of being hit by extraneous debris, and if it had a metal composition, obviously to be suitable to weld. The team decided on a piece of debris from the Delta I satellite. With the target debris decided, we move into stage 2, launch and rendezvous. Prometheus is going to launch from a Falcon 9 from Vandenberg and eventually rendezvous with the target debris. Using our robotic arms, we'll then capture the debris, and then we'll begin to laser cut operations to create a clean welding edge. So the rendezvous and the laser cutting operations are semi-autonomous with a command signal given. And once laser cutting operations are complete, Prometheus will fold out a plate from its body for the debris to be welded onto, and that will all be completely autonomous. The payload welds the debris onto the metal plate using electron beam welding. And finally, the payload will perform a brief test of structural integrity on the weld and communicate mission success with the ground before deorbiting. Next slide. So I'll now talk a little bit about the analysis work we completed for the Prometheus payload. We'll start with first the laser cutter system. After completing a trade study against 2 other laser cutters, the fiber laser cutter was chosen for its power efficiency, its cutting speed, and its size and weight. So what we see here is that the diodes are produced to pump light. It's then directed into the fiber, and the ions in the fiber get excited, and to get back to their low energy states, they're producing a lot of light emission. This causes a chain reaction, and then we get into these Bragg gratings that are going to reflect the light and just ultimately build up all of the light that we're forming to let out into a laser beam. And there's the lens at the end of the beam to really focus this and get a precise cut with minimal. Next slide, please. And then for our welding apparatus, this was also selected through a trade study against 3 other apparatuses and was ultimately selected for its beam current, beam power, and mass. The electron gun design chosen comes from efforts made in electron beam welding technology by B.E. Patton. Patton designed this new electron beam gun for the use of in space, intended originally to be used manually by astronauts, but our mission looks to reconfigure the electron beam gun for robotic arm manipulation. So we first start with a power converter applying high voltage to the cathode. We excite electrons, create an electron beam directed at the anode. Then because of the efficiency in the cathode's chemical compound, we're able to actually only use 30 to 40 watts of power for this heating. To withstand the 10 kilovolt operating voltage safely, we have a high voltage insulation. It's made from aluminum oxide, which is known for its mechanical strength, high resistance to voltage breakdown, and low thermal expansion coefficients. So this paired with other metal alloys are paired together and are vacuum sealed together. And then for better power density, a control voltage of 4 kilovolts is applied. This is going to shape the electron trajectory to form a highly convergent beam. In this system, the power density can be up to 16 kilowatt per millimeter squared, which allows us to weld 6 millimeters thick. And altogether, this really only weighs 1.8 kilograms, so it's great for our mass budget here. Next slide. In terms of down selection for the robotic arm, a trait study was completed using a series of robotic arms that have already been used in previous in-space missions. So our trait study prioritized payload capacity, range of motion, and autonomy and control modes. And from this, we ended up selecting the MDA arm, which we have a CAD model down there, integrating that with our payload. Next slide. We then completed an FEA analysis for our payload experience in launch conditions through SolidWorks. We're simulating launch conditions from the Falcon 9, and we're only seeing really low deformations on the scale of micrometers. So we're pretty certain that structures are not going to fail throughout this mission if this is the only deformities we're seeing in the launch conditions specifically. Next slide. For our thermal cases, there were a lot of hot and cold cases performed specifically on the payload. We're looking at active and passive control systems and using a lot of these details from the SNAP book that we were referencing multiple times. We were able to come up with a pretty intense thermal control for our payload system. Next slide. So we can now take a little closer look at how data is transferred inside the payload. From the Venus X-class bus's communication subsystem, we've outfitted that with an antenna that we've trade studied down. Our payload has its own computer that will receive the initial start command to begin our mission operations. The command and data handling subsystem is going to send its status data that debris is nearby. This is going to engage the robotic arm. The arm will then send status updates to the laser cutter and confirm debris capture. Then the laser cutter system will send its cutting status with the welding subsystem, and then it will engage and send its own welding status updates back to the command and data handling subsystem. At the same time, the power and thermal subsystems on board continuously send status data to confirm we are not overusing power or overheating the payload. These two forms of data are sent back to the Venus X-class bus's communications subsystem to send to ground at the next pass. Next slide, please. So we're going to be working with the Abu Dhabi ground station for this mission. The image on the right shows the orbit of the Delta I debris and its intersection with the ground station. We have available to us 38 passes a week with an average contact duration of about 15 minutes. So most of the data that I just mentioned is basic telemetry and status data, and that one final piece of raw data from our structural integrity test. There's only a small amount of data per pass that we're going to be sending down because of this. So we're looking at about 50 kilobytes of that and about 10 megabytes for the structural data. Putting this together with our 38 passes per week available to us, we're looking at about a downlink data rate of 5.28 megabits per second. And on the bottom, we can see a small sample of our link budget, and we do have some more details about this later in some backup slides if you're curious about any other confirmation on where we're getting our really high link margins from. Next slide. So the power budget for the Venus X-class bus and the Prometheus payload are both shown on the right. The power budget specifically looks into the max instantaneous power consumption during daylight and during eclipse times, and we found these eclipse times specifically through an analysis on SDK and MATLAB. So we're looking at, during our really high machining operations, an average power consumption of 305 watts, and during this eclipse times it's significantly lower because we're just in a sleep mode. We're only looking at thermal and power subsystems to keep our payload thermally regulated. And to fully charge, looking at this power standpoint, to fully charge and get up to here, we're looking at 122 orbits, which will take about 10 days. Next slide. For our guidance, navigation, and controls pipeline, we've considered AI methods for efficiency and flexibilities. These are still being developed, and we'll talk a little bit more on, as these are things that we'll have to develop in PDR. But the sensors we're going to be using aboard these missions obviously are standard sun sensors, gyroscopes, magnetometers, and our own cameras for this. You can go to the next slide. So our mass budget is originally composed using a bottoms-up technique, using a percent breakdown estimate from the SNAG book to give preliminary subsystem mass budgets. But then as we developed our pieces and the equipment that we'll be using for this, we were able to get a top-down method, which you can see in more detail here. We're clearly underweight. We are at 46 kilograms. So even with a 20% reserve, that's only about 9 kilograms more to add to this mission. We are well under the 70 kilogram budget. Next slide. So here's a 3D of our payload. The Prometheus payload fits exactly in the 17 by 16.4 by 27 volume constraints. And we can see a little bit more about the flexibility and the range of motions in the arm. You go to the next slide. So some things to point out about our payload: will be using aluminum 6061. It's obviously very robust for space flight. It's been tested a bunch of times in space. Its primary use is in space. We'll be utilizing these two robotic arms, one with the grabber at the end and one with the electron beam welder and the laser cutter at the end. So you can go to the next slide and we can see an animation of sort. I think it should be embedded. Yeah, so we see the rendezvous with the debris, then the deploying of the welding panel using linear actuators to move the clips. And we have rotary actuator discs to rotate the panel from the body. And then the debris is brought down to the hole where the laser cutting is going to occur. Doors are going to be placed here to keep laser cutting debris inside, and then the panel is brought up to the welding plate for welding to occur. Perfect, next slide. So some of the technologies we're looking to use that are not quite ready for this mission would be the current fiber laser cutter. Right now it's just a little too big to properly integrate it with the payload. What we need is a small scale fiber laser cutter designed to fit onto a laser cutting gun. This would enable cleaner laser cut edge and improved precision of welding with minimal waste production. Another technology gap would be for fully autonomous adaptive servicing system. Currently, servicing systems are not able to do any kind of adaptive decision making or autonomous monitoring, so we're looking into achieving something more on the granular scale for that in the upcoming years. And finally, another technology we need to be developed by end of decade is a compact high energy battery cell. Our current batteries are too heavy or lack energy density for our mission operation without frequent recharging. It's going to take a while to do that. We need a battery with sufficient energy density to sustain laser cutting and welding for extended periods without needing to recharge frequently. This way we can decrease our mission duration by a lot. Next slide. So throughout our design process, we've encountered a lot of challenges. I'll introduce some of them here, and then we can talk about the risks that these challenges pose to our mission and how we've decided to mitigate them. First is the lack of heat dissipation in the fiber laser cutter and the electron beam welder. We've not been able to find a solution to directly preventing overheating in the laser cutting and welding, in the laser cutter and welder. Excessive heat could obviously melt the gun tips and potentially even interfere with our sensitive payload electronics. Without mitigation, the duration of laser cutting and welding operations pose a risk to onboard equipment and mission success. Second is the power supply issues we've had with the DC-DC converters. Laser cutting and welding are very power-intensive operations, and currently the battery we have on board does not have enough power to support. At this point, we also have been unable to find a DC-DC converter for the battery that has been tested in space or for space that meets our operational requirements. And finally, we've had challenges integrating debris mitigation into our plans. There is a risk of debris generation, especially during our welding operations with small splatter debris. Large debris generation by the mission is clearly, debris generation by this mission is clearly not satisfying any of our mission objectives, and it poses a hazard to both our payload and surrounding components. Next slide. So the challenges I just mentioned are shown on this table here as risks 2.1, 3.0, 4.0, and 5.0. So we can take a moment to go through the biggest risks of our mission. 1.0 is any type of autonomy failure. Obviously, in the case of an autonomy failure, the mission is not going to be completable and is therefore severe in impact. If there is an autonomy failure, there's no choice but to enact a manual override contingency. And with this in place, there's obviously no probability of autonomy failure happening again. So this is a risk now that is now in a green section. You can see that 1.0 move from red to green. Risk 2.0 is about our payload hitting debris, and it's divided into two sections. 2.1 is what we talked about previously on self-generated debris. This has the potential to severely impact mission status if the payload is damaged, and is very likely to occur because of the nature of welding operations that typically splatter. Our mitigation strategy that we've been working on for the last month or so has been to contain the laser cutting procedure inside the payload, which you saw in our animation. This will allow any generated debris to not harm the payload and also allow us to collect self-generated debris and not release it back to LEO. This mitigation strategy decreases the amount of possible damage, lowering the severity score from severe to moderate, and having debris contained decreases the possibility of occurrence. Risk 2.0 on the other, 2.2 on the other side is hitting external debris during rendezvous. If the piece of debris is near other large pieces, this would be a likely occurrence and have significant impact on the structure of the payload. Imagine you go out, you rendezvous, and the payload hits you instead of you grabbing the payload. Bad news. We've mitigated this risk by rendezvousing with a more isolated piece of debris for this demonstration mission. Like I previously mentioned, we'll be looking to rendezvous with a piece from the Delta One satellite. Expanding this mission beyond its scope to perform ISAM operations in more debris-dense areas in LEO would require more protection on the body of the payload, specifically in the robotic arms performing operations. Obviously, these are really intensive operations, and those are very easily damaged parts, so consider more protection over those areas. As it stands with this mission, by rendezvousing with isolated debris, we've lowered the possibility of being hit by external debris. Risk 3.0 is another challenge we just talked about, insufficient battery charge, and our plan for this is just add an additional battery, quite cut and simple. We have the mass for it, we can have another battery, and we've now lowered our probability rate for that. Risk 4.0 for overheated internal parts, we'll be looking to increase radiation hardening and thermal coverage near the laser and welding arm. So this is a little bit more delicate in terms of increasing radiation hardening might mean different things for different parts of our mission, but overall, we're looking to have that, although the severity remains the same for overheated internal parts, by increasing radiation hardening throughout the payload, we're looking to decrease the probability from likely to pretty unlikely. And then for our final risk for a low technology readiness level, this is in terms of our battery and our DC-DC converter not really being tested in space yet. We'll just have to have additional component testing within space conditions throughout the next 5 years to meet end of decade requirements. Next slide. So after designing our top level requirements last semester, we looked into various types of welding and ways to demonstrate the weld. The concepts seen here were eliminated from our consideration during our concept down selection, but they do show some of our more innovative concepts. On the left is a concept design for laser welding directly onto the body. Laser welding uses fiber laser for welding and laser cutting, which eliminates the need for separate attachments on the same arm, which is incredibly convenient. The design also welded directly onto the payload, which removed a lot of the mechanical complexity of dealing with the test plate. On the right is a concept design for arc welding onto a separate plate. Low pressure arc welding begins with the welding arm heating and extruding metal points along connection points, and then it just bonds the test plate and the debris. Doing this procedure on a separate plate was great for keeping high heat operations away from payload equipment, obviously a big concern of ours. But this concept design required a third arm to grab the test plate, which can be good for redundancy, but ultimately it was a little too much maneuverability for us to comply with this mission. We eventually went with a design using electron beam welding with a folding plate, and we are now creating compartments, and we have a compartment to perform laser cutting and welding operations internally, which makes our mission more unique and stronger in debris mitigation. Next slide, please. So since completing our concept design review in March, this team has been making considerable progress towards a preliminary design review. We've completed significant analysis, mostly through trade studies, to integrate the Prometheus payload and the Venus X class class. We've incorporated communication, command and data handling, GNC, structures, propulsion, thermal, and power subsystems into the bus. You can see a little bit of the FEA that we have performed for the Venus class bus on the side there. We've also performed analysis through ANSYS's SDK to determine the mission's launch site, ground station, and perform a really detailed orbital analysis. Next slide, please. Beyond integration with the Venus X class bus, to reach PDR, a considerable number of other steps need to be taken. First, the code responsible for the arm needs to be developed. This will need to allow the arms at least 2 degrees of motion. The electron beam welding gun also needs attention with more detailed plans for integration of the gun's payload. And of course, the mission needs to continue to work to close the technology gaps I mentioned earlier, which includes performing more testing on the battery and converter aboard the payload to increase its TRL. In reaching a preliminary design review, other things to be considered developing along the way to be ready for launch at end of decade are a bill of materials, plans for manufacturing parts for prototype, testing that prototype, and overall AI development. The payload's basic bill of materials is shown on the right here, and at the bottom includes the launch vehicle cost. So we're looking really simple, basic bill of materials here. Next slide. So the first, we're going to look at our lessons learned, and we'll talk about this in 2 sections. Firstly, will be on our specific subsystems and work-oriented tasks. taking material learned previously and applying these learned principles to the project is pretty important for us. So for example, past thermal classes that we've all taken provided a generic overview of thermal analysis. However, this project has allowed us to do a lot of hands-on work in a more detailed task, from creating thermal models throughout flight to identifying hot and cold cases to looking into specific coatings for optimal thermal regulation. And what we see down here, second section and group specific, we've learned a lot of things in terms of how to create a professional workplace environment that encourages productivity and how to effectively communicate to apply certain techniques. Next slide, please. So to conclude, I want to rehash some of our key innovations, which would be our semi-autonomous laser cutter and our autonomous electron beam welder manipulation, and integrating those both onto our robotic arms, and our debris mitigation plan to perform our high-intensive operations within the body of the payload. And overall, our impact on ISAM will be advancements in welding and laser cutting automation, which are really key parts of servicing, assembly, and manufacturing on Earth, and eventually in-space testing of lightweight electron beam emission systems. We can go to the next slide, but I'd now like to invite my team up to answer any other questions that you guys may have.
Okay, if judges have any questions, if you're online, just speak into your computer. If you're in the room, come up to the front and take the mic to ask the question. So I know for this demonstration mission, there's a limitation on the size of the debris you can capture and cut because you need to be in an enclosed volume. If you wanted to scale this up to do larger debris, how would have you thought about ways you could contain the debris without just making the satellite bigger and bigger?
It hasn't been something that we've directly thought of, but for the possibility, maybe if we did do larger debris, adding a third arm possibly would allow for a second point of contact onto the debris. The other thing is just making the arms a little bit more robust. It's not something that we directly thought of.
Yeah, and just to tie in, if you saw the last briefing yesterday, like Space Bender, I really like their idea of making large structures. They presented it first truss, but I think these ideas as well as you could make like a large enclosure, just for the outer enclosure, you just need a frame and then something to put around it, and then you could do operations inside. And that's why I really like seeing all these presentations one after another, because it gives me ideas about how one can help the other. That wasn't a question. So do any other judges have questions?
Yeah, we got one, Jacob.
Yeah, I was wondering what consideration you gave in your trades for the robotic arm in terms of how long it should be and what kind of workspace that provides your system.
Sorry, could you repeat the question?
Yeah, I was wondering, was there any consideration in your trade studies for the robotic arms that you chose, how long it should be and what kind of work that affords the robot to be able to perform?
In the original trade study that we conducted, looking at the arms, we're basing on the designs aspects of it, and then once we selected the preliminary design, we scaled it down so that it would be more appropriate for our scale for the NSM mission.
I think it was 1 week. Go back to it's on our slides. I don't know which slide it is.
Any further questions?
Did you want to ask to go back to this? Yeah, we can show it on the screen. If you want to go back, we do have the trade study actually in our slides in the robotic arm subsection slide. I don't know what slide it is. No, it's slide 9. It's in slide 9. So if we could go back to slide 9, we can see. Yes. So that shows a little bit more of the criteria.
Yeah, so on the top, you have the different type of arms, and then based on the criteria we selected, it gave us the best score for the design arm, but then we had to go in and make it our own so that it would fit our model.
Okay. I want to thank Team Prometheus once again. It's a great presentation, like they all have been. And why don't you guys stay up there for your photo, and then. Yeah, and then we're gonna break for lunch, and we will be back at 1:45 Eastern, 10:45 Pacific, and we'll try to start right on time. So thank you, and we'll see you after lunch.
I think that may be a go.
Good afternoon. I'm Nicholas Luis. I'm here with Nicholas Sternberger, and we're representing our team, Leonis from Penn State University. And we're going to be talking about what we call the DISC mission, which stands for Demonstration of In-Space Coatings. Next slide, please. So, a quick background. Spacecraft require coatings to better survive the space environment, whether that be from extreme temperatures, extreme radiation, or even atomic oxygen present in low Earth orbit. And even a thin coating, also called a thin film, can significantly alter the material properties for this application. Satellites you see on the right, those are coated in what seems like a gold foil. It's actually insulation coated with a very thin metallic layer. Currently, there's no way to apply or reapply these coatings while you're up in space, which hasn't been an issue too much in the past because you just coat things on the ground before you launch them up. But now with recent ISAM developments, we now have things that are being manufactured or planned to be manufactured in space, as well as expensive satellites whose coatings have degraded that need to be repaired. And our mission aims to fulfill this technology gap by acting as a technology demonstration for autonomously manufacturing these thin film coatings in space. And we will do that using the following three operations. First, we will grab onto objects. Second, we will coat objects, and we have the ability to coat in both aluminum and chromium. Aluminum was chosen for its high reflectivity in both the infrared and visible spectrum, and chromium was chosen because of its stability against atomic oxygen. And our third operation is to analyze surface properties in a process known as surface characterization. And next slide, please.
So our team has 7 members, including our team lead, Nick Luis, who you just heard from, Jason, Miguel, Noah, Caden, Luke, and myself are also part of the team. Next slide, please. So we hit some major systems engineering milestones throughout the year that we've been developing this project. Back in September of the fall, we selected Nick as our program manager. He has the most experience with physical deposition and the actual coding process, which is why he was selected. Moving into September, we did a lot of extensive research into ISAM as a whole, and this is how we found the technology gap that we need to be able to coat things in space in order to manufacture. And we ended up choosing our 3 ISAM capabilities, being able to handle the object within the payload, being able to code it, and being able to analyze the surface in a way where we can confirm that the coating achieved the desired material properties. And then in October and November, we defined our system requirements, starting with our functional analysis, as well as top-level requirements. These requirements and these constraints ended up driving our subsystem design this semester. In December, we completed our full ConOps, which also had the 3 innovative concepts, which we made our final concept down selection from a matrix from the ConOps. We completed our C3 flash talks and also completed a system requirements review. In the spring, we did a subsystem decomposition, breaking the subsystems between the team members. We ended up integrating them after extensive research and trade studies were completed to make sure that they met the system requirements. And then we began developing our path to a preliminary design review. Next slide, please. This is the storyboard of our complete operation. It begins with a launch from Kennedy Space Center. We're going to be using the Falcon 9 rideshare program. We also selected an orbit that will allow us to launch from Kennedy and inject directly into our orbit from the Falcon 9 rocket. Once we have verified that we are on the correct orbit and we have made uplink with ground station, which I'll talk about a little bit more later on, we will conduct the 3 operations, coating in both aluminum and chromium, and there may be some time in between coating with each material to recharge the battery that we've included within our payload. Once we have confirmed that we've successfully coated in both aluminum and chromium, we're going to move to deorbit or into a graveyard orbit. Next slide, please.
So on the right here, you can see a labeled diagram of how our payload is kind of situated. It's split into 2 main chambers. We have the coatings chamber on top, shown in purple, and then it's separated from the electrical box, shown in green on the bottom there. And it's separated using insulation as well as heat piping. And some important aspects of this payload are labeled. We have the target object or the substrate that's going to be coated. In this case, we're just using a simple cube as a demonstration. And it's being held by 2 robotic arms. And it'll be lowered in between the 2 telescoping arms that can move it left and right as well as rotate it. And then below that, we have 2 crucibles that will perform the coating process. Those 2 are placed on a slider that can move into and out of the page. And finally, below that is the sensors located in the electrical box, which can see into the coatings box through like a small glass window. Next slide, please. And if you could play that animation. So as you can see, that's our first operation, grabbing onto the object. And then we coat the object, moving it left and right, as well as moving the crucibles in and out to coat that entire bottom surface of the object, often pausing briefly at times to scan and analyze the surface. We're also able to rotate the object using those 2 telescoping arms and rotators, as you can see there briefly. And then at the end of the operation, we grab the object again. Next slide, please. So going into a little more detail on the operations, the robotic arms we're using are modeled after the Mitsubishi RV-2HA. It's 5 degrees of freedom, and that lowers it into the 2 telescoping arms with 2 degrees of freedom. Makes it a little more limited, but it has it's more robust and has active cooling to better survive the coating process, which we'll talk about in a minute. Next slide, please. So our other operation is surface characterization, and the purpose of this is to analyze the surface to identify if we have correctly coated the surface. And this will be done using the following 3 sensors. First, we have a laser interferometer. Not going to go into the complex physics on how it works, but it's essentially able to measure distances up to 1/2 the wavelength of light that you're using. In this case, we're going to be using visible wavelength light, so we can take surface roughness measurements up to about 200 nanometers. Next, we have a simple white light emitter and receiver. It works by shining a light onto a surface and measuring how much light has returned, and that measures reflectivity. And finally, we will have a camera equipped with image recognition software or even possible human operation in the event that things go wrong. And with all these sensors, we're operating under the assumption that we already have the data to compare our results to. So, long before launch, during the testing phase, you would coat something and analyze it with the sensors, and that data would then be uploaded to the onboard computer for it to autonomously determine if the coding process has succeeded. Next slide, please. So speaking of the coding process, we want to coat using what's called the evaporation method, and it was chosen because it was well understood, mature, and it's a relatively simple technology. The way it works, you can see a diagram on the top right there. You heat up a material until it evaporates, and the evaporated gas is then condensed back into a solid once it makes contact with the target surface, or the substrate, it's called. For our case, we're going to be using a crucible, like you see in the bottom right. And that's going to be the source of the evaporated material. We're going to have either aluminum or chromium inside of that. And it has a small opening on top to let the gases escape while keeping the liquids inside. And there's a groove around the outside to allow a coil of wire to be wrapped around it. And to heat up the crucible, you just pass a large current through that wire, and it would heat it up using resistive heating. And for our crucibles, we chose two materials, boron nitride for evaporating aluminum, as well as vitreous carbon for evaporating the chromium. And those were chosen because it was pretty much industry standard for using those materials for our specific applications. Next slide, please.
So we faced a couple of big challenges throughout the development of our project. The first, and definitely the most prominent one, is actually regulating the temperature within the crucible and within the payload. During our initial estimates, we found out that the crucible temperature for either material needs to reach 1,650 degrees Celsius, which is quite hot. And in order to we needed to keep that heat from actually leaving the crucible and propagating to the actual structure of our payload. The second challenge that we faced was actually generating the required power output necessary to heat the crucible to this temperature. We estimate that it'll be at least 415 watts, potentially more, which actually pushes the limitations of our solar cells that are on the Venus class bus. And the last challenge that we faced was actually understanding how this evaporation process will change with microgravity. We have never performed the evaporation method under microgravity before. We do know that the quality of the coating is relative to the quality of the vacuum, but we do not know how the actual microgravity will affect the movement of the gases towards the target substrate. At the bottom of the slide, you can see a picture of the heat shield that we briefly designed for the crucible. It is made out of materials that I'll discuss on the next slide. If you could go to that, please. So a little bit of information on thermal subsystem because it's so important for the success of our mission. So we're going to be using a heat shield around the crucible. It is made out of molybdenum, and the outer shield is made out of an H.A.D.E.S stabilized zirconia. They're highly insulative, so it'll keep the temperature hopefully isolated to the crucible and not allow it to harm the structure or the electronics within our payload. Also within our payload, we have some copper heat pipes. We found a good example of these from Advanced Cooling Technologies. We would use a similar thing here. And then lastly, we also have the radiator, which is located at the top of our payload. The one seen on the right here is from Sierra Space and actually has perfect dimensions to fit our payload as constructed. We're going to include a couple other thermal controls within our payload, including thermostats that will allow our onboard computers to actually autonomously keep the temperature at a reasonable range for the rest of the structure. Next slide, please.
So this being a kind of novel technology, there are some risks associated with it. And as a team, we discussed some and then plotted them on a risk matrix based on their probability to happen and the consequences if they were to happen. Now, some of these are pretty typical of satellites, such as sensor malfunctions or electronic failing due to radiation. But some of these are also very mission specific, such as molten metal escaping in microgravity, the crucible heating element burning out, or damage at the target substrate. And we did discuss some mitigation for some of these. For example, with the molten metal escaping, the crucible was specially designed to keep the liquid inside. But in the event that it were to escape, it could damage electronics as well as gum up some of the moving parts. And we did discuss ways to fix those issues. For example, with the moving parts being gummed up by solidified metal, a way to get around that is to slowly move the motors back and forth to kind of break up that blockage. And that's a pretty tried and true method, actually, as demonstrated by the Ingenuity helicopter on Mars, which was able to survive a dust storm by moving those rotors back and forth to break up those blockages. And next slide, please.
So we're going to talk a little bit about the data handling and communications for this mission. So we selected for our ground station Amazon Web Services, or AWS. They have a ton of locations around the globe, which was great for any type of downlink where we are sending our data down to Earth. The three main locations that we're using are in Ohio, Ireland, and Bahrain. And these three locations really line up with the evolution of our ground track over the course of our mission. For the downlink, we actually don't need to be in communication for downlink that often. Most of the data processing and storage will be actually held within the payload itself. For the downlink, we selected a 3.5 megabit per second bit rate. This will allow us to send the photos as well as the coding data on top of the telemetry data that we're going to be sending. This came out to a link margin of 25.07 dB, which again, both our link margins here are really high. So adjusting some of those values as we move towards actual prototyping might be beneficial here. For the uplink, we selected a 1.5 megabit per second bit rate. We're really only going to be sending commands, with the 3 commands highlighted in the flowchart on the right being the only primary commands being sent to our payload. And then for the onboard computer, we ended up selecting the Antelope computer from KP Labs, which is a company based in Poland. It has extremely high data processing speeds, great flight heritage, and its 8 gigabytes of DDR4 memory and 48 gigabytes of flash storage are essential for us to process our coding data and store it within the payload itself. Next slide, please. So a little bit about our path to the preliminary design review. We want to talk a little bit about the integration with the Venus-class bus. So we assumed that we were likely limited to components that were actually provided by VCT, and so we selected certain components from their catalog to incorporate for our mission. So we ended up choosing the Flex Core attitude control system because of its high pointing accuracy and its low error rate. For the Star Tracker, we went with the standard model. There wasn't a huge difference in performance between the different models, and it had the lowest effect on our mass and power budgets, which you'll see is important in just a few slides. The reaction wheels, we went with the RW8 model as it had the highest torque capability and also the lowest power requirements, which once again is extremely important for us. For the antenna, we went with the S and X band all metal patch. This allows us to communicate at the 2 frequencies that AWS can communicate at. And so it had the right operating frequency for us. And then for the thermal design of the bus, we were kind of going just with the standard thermal design. We don't expect the thermal parts of our payload to actually propagate beyond our payload itself. Next slide, please.
So we will be supplementing the dual solar panels with a battery. And as you can see here, this is our trade study to determine which battery to use. We compared a lot of different models based on their capacity, storage, their mass, and their temperature range, etc. And we ended up choosing the Eagle Picture Technologies 60 amp hour battery. For reasons we'll get to in a minute. Next slide, please. So as you can see in the middle column, that's the power budget when the coding system is inactive. We're dedicating about 300 watts to charging that battery. But when the coding system is active, as you can see on the right, we're using about 415 watts for the coding system, and that's just to maintain that 1,650 degrees Celsius temperature for the crucible to operate at. Next slide, please.
All right, this is the mass budget for our mission. So for the mass budget, we primarily took estimates from other small sat missions, but also took some liberties because our mission has never been done before. So for the structures, we went with about 30% of the total mass of our payload. Our structure of the payload is aluminum 7075, and we've also designed a small support lattice. We allocated the most mass after the structure to the coding process, as almost all of the instruments within the payload outside of the sensors are for the coding process. We are significantly below the maximum mass that we allowed of 70 kilograms for the payload on the Venus bus, including a 15% contingency margin. So we have plenty of room to add components as necessary, as I think there will be more thermal control when we move towards prototyping. Next slide, please. So a little bit about the innovative concepts that we generated throughout this project. We generated 2 concepts that we didn't end up moving forward with. The first is the external coding method, which can be seen in the top 2 photos on the right. It attaches, after rendezvousing with a satellite, it attaches to the outside of the satellite using an electromagnet, and then using a small roll wheel, it would move along the external part of the spacecraft and code it as it moves. The benefit of this model is that it's better for servicing older spacecraft or anything else that needs a coding to be applied in space. The second method is the hybrid coding method. This is seen in the bottom 2 pictures on the right, and it is unique as it happens external to the payload as well, but we are once again storing small to medium objects with a robotic arm. During the coding process, it also deploys a protective cowling to ensure that we are not releasing molten metals into space. Next slide, please. All right, we also analyzed some technology gaps that would be really beneficial in the potential success of our mission if these gaps were acknowledged. The first is thermal management for internal high temperature systems for really small volumes. Spacecraft hardware has yet to prove the capability to handle temperatures potentially exceeding 2,000 degrees Celsius within a small volume without actually destroying the payload structure or sensitive electronics. We also had no precedence on how our coding application might be integrated into future ISAM workflows, or such as an assembly line where something may be 3D printed or manufactured in space, and they need to code it before it can actually survive the space environment. And the last part was that there is currently no proven method for how to handle those molten materials in microgravity, or in what ways they might interact with the rest of the payload. Next slide, please. So a little bit about our paper. It goes into a lot greater detail about some of the design decisions that were made, including trade studies. It also goes into greater detail about the coding process, such as how we calculated how thick the coding will be, or how much we're going to generate in a certain time frame. The abstract is about 200 words, with the total paper being about 20 pages, with 22 references, and we're going to be publishing this to the AIAA SciTech conference in January of next year. Slide, please. So a little bit more about our path to the preliminary design review, some future work that we have highlighted that we would do in the future. We would like to look at some buses that maybe have some larger power or size capabilities. This will enable us to have better thermal management within our payload, as well as being able to produce more power and potentially cope with even other materials. We would like to do some on-the-ground testing with the Antelope computer using the sensors that we're going to have on board. It'd be nice to have that backup data so that we can actually generate those algorithms that would allow our computer to autonomously determine whether our coding has succeeded or failed based on its meeting certain material properties. We would also like to do some vibrational launch testing for ride sharing aboard the Falcon 9 rocket, as well as working with VCT on full integration with the Venus bus, and overall revising the design of our payload and improving the robustness of our arms and other moving parts. Next slide, please.
So to conclude, in-space codings are a necessary enabling technology for future ISAM capabilities. We see this being used maybe in like an assembly line, like you said, where spacecraft manufacture something and send it to us to be coded, and then so on and so forth. In fact, earlier this week, I saw another team present a concept on how to 3D print large objects in space. So it might integrate with that pretty well. Or even objects that are not made in space. Satellites whose coatings degrade over time, that needs to be repaired. And there's even evidence to suggest that thin film coatings that are done in space will be higher quality because of the vacuum of space being orders of magnitude better than any commercially available vacuum here on Earth. And while doing research for this project, we also saw that there was a NASA publication suggesting it could be used for some cool sci-fi technology like solar sails because of its ability to manufacture very thin layers of material. And throughout this project, we learned a lot. First, we used a lot of commercially available parts instead of designing everything from scratch. This was very helpful, especially in this conceptual design phase, because it reduced risk and gave us a lot of understanding. For example, sensors and the other instruments and robotic arms, for example, we knew exact dimensions, weight, operating temperatures, all of that. Next, having a coatings expert more closely involved in the project would be more beneficial, because while we did have a coatings expert that we consulted, late in the design phase, there was questions we didn't even know we needed to ask early on. Having a coatings expert on the team would be able to spot those things right away. And finally, simply the interdependency of our subsystems is a big thing we learned. we change one thing like the crucible, and then all of a sudden it changes other subsystems, like how much power we're going to use and how much thermal management needs to be done. Next slide, please. And with that being said, we'll take questions now.
Okay, do we have any questions from the judges?
Yeah, I have a question. Can you hear me?
Yes, we hear you.
Yeah, Vinay Goyal here. Question about when it comes to coatings, one of the concerns that people consider is the differential thermal expansion. So the application of that material first and ensuring that the material can stick, but then also how do we ensure the quality of that interface, and then finally how it performs due to the on-orbit thermal cycling that will occur, that which could then lead to spallation. So could you kind of address how you go about thinking about that?
Yeah, so we didn't really think about differential thermal expansion during this design review, but that could be something that's done in the next steps. Part of a testing phase. Coding things on the ground, testing the kind of data that you get from them, and then that kind of gives us an idea of what kind of data indicates a successful coding. And in terms of actually checking up on that coding later on to verify that it's still properly applied, we can just use the onboard sensors once again. Hope that answered your question.
Also, one other thing for that question. When we were designing the custom-made crucible that we designed for our payload, we also thought about potentially putting a mesh or a slider over the hole to potentially try to prevent that liquid from escaping if it were to try to escape. And we've also discussed not using a significant volume of the crucible for the material to allow it to have that expansion room.
Okay, yeah, thanks for the response. What about verifying quality after you apply the coating?
Are you talking about verifying like thin? Oh, verifying, sorry. So verifying after, yeah, that's part of our con-op. So if you could go to slide number 5. So we analyze the surface both before and after the coating process. And we compare the data, and given we have the data already on board, we can properly process it and categorize the coating.
Okay, but when you coat the surface, isn't there an interface that forms between the coating and the substrate material?
I'm not sure if that's the case with this process, because the material we're coating with, like aluminum, it would just condense back into aluminum once it makes contact with the surface. So I don't think there will be an interface in between.
Not an interface, but there needs to be some amount of fusion or some amount of strength that occurs when you apply coating to the substrate.
So like adhesion between the coating surfaces, right?
Yeah.
Yeah, so that would, you would have to choose this mission to be done, on very specific materials that it will bond correctly. You can't just use, any material with it.
Also, from the laser interferometer, we get some surface roughness data, and so if we program the algorithm of our computer to code in a way that it emphasizes that surface roughness data, we can also enhance the adhesion that way.
All right. Well, thank you. Appreciate it.
Thank you.
Okay, we have time for one more question from the judges.
I got one. Can you clarify the grab part of the capabilities? Are you grabbing something that is free floating, or is it something it's a fixed object? And depending on the answer, have you thought about the applicability of coding, on orbit objects and what you would need to do for your system?
We haven't talked about potentially moving objects on orbit. I know we meant it more as moving as in like moving it from the robotic arms on the top of our payload towards the telescoping arms where we were going to be coding. But once that they reach the telescoping arms, the only thing that we're going to be doing is moving them within that XY plane and then rotating.
And then I would maybe address the free-floating or fixed object part of that question.
So we, at some point in the design phase, we have potentially considered having bay doors at the top of our payload that would actually have the objects move in and out of the payload. For example, with the assembly line where something would be sent to our payload to be coded. And so that's something that we looked at. We primarily looked at it using like a tether. We didn't necessarily want to release it free floating and then try to move to catch it, as we felt like there was a high risk of us potentially just missing the object that we had spat out. But we did look at that partway through.
Okay. I think like we've run out of time, so let's thank our team H.A.D.E. Leonis. You guys pose for your photos, and also when you're done, check the Zoom. There are a couple of really good questions in the chat for you.
Awesome. Thank you guys.
Sorry. There you go. Thank you guys. Yes, we have Katie. Yes. Yes, I will. Yes. I thought so as well.
Okay, next up we have Team H.A.D.E.S with Project H.A.D.E.S from the great state of Virginia, as they say. And you guys, whenever you're ready, can get started.
I'm sorry, could you say that again?
Oh, yeah, like they're good to go.
Okay.
Team H.A.D.E.S can get started.
Hello, everyone. We are Team H.A.D.E.S from Virginia Tech, and we're excited to introduce Project H.A.D.E.S, which is an autonomous space manufacturing and assembly payload. Next slide, please. Project H.A.D.E.S centers around directed acoustic energy deposition, or DAED, which is a novel low-power additive manufacturing method. Once using this method, we're going to print small aluminum cylinders that we're going to assemble with precision laser-based welding systems. And we'll also employ AI-powered defect detection to make sure there are no errors in our system. Next slide, please. Our team is split into 5 sub-teams: autonomy and control, thermal and power, additive manufacturing, modeling, and systems engineering. And we're all students from the Aerospace and Engineering Department of Virginia Tech. We were mentored by our faculty advisor, Dr. Kevin Shinpa, and our industry advisor, Dr. Randy Spicer of Northrop Grumman. Next slide, please. The backbone of our system is the Blue Canyon Technologies Venus class bus. The main constraints we had were the energy storage, volume, and mass. We did some more research into the Blue Canyon Technologies satellite, and we found a NASA document that said it actually had a max payload mass of 78 kilograms, and it only supplied a power of 60 watts to the payload. Next slide, please.
So we considered a few different concepts in the beginning of our research development. These include reusing Earth's plastic waste as filament for additive manufacturing, space surface coating for repair applications, and joint system for assembly without fasteners inspired by traditional East Asian architecture. After reviewing the feasibility of each of these concepts, as well as our interest in manufacturing, we decided to move forward with in-space additive manufacturing. Next slide, please. So Project Daedalus is a is a proof of concept of metal additive manufacturing and assembly of objects in space. So furthering of this technology can directly optimize structures for the space environment rather than having to deal with launch constraints such as launch loads and payload volume allowment by the launch vehicles. Traditionally, large-scale spacecraft such as James Webb Space Telescope would need to be creative with how they meet these requirements by, in their case, using origami-like folding. But with this technology, the structure can be directly assembled in space without having to deal with these constraints. Other impacts of this technology would be on-demand part production for satellite repair, as well as supporting newer improved types of spacecraft. Overall, this technology would be increasing satellite lifespan, as well as furthering our knowledge in space capabilities. Next slide, please. So our Project Daedalus's mission is outlined here in our concept of operations. Starting with launch in 2030, we arrive to low Earth orbit, and we get to step 1, which is orbital deployment and solar panel deployment. If we zoom into the BCT bus payload, we can see the configuration of our additive manufacturing components. And then we move on to step 2, which is initializing the system, where our system moves out of the launch configuration and the status is downlinked to the KSAT ground station network via S-band. Next step is initializing the print, so the print head is lowered to the print bed and the DAED components are initialized. Then our metal DAED printing operation is performed. For the first iteration, this would be a 3-inch tall, 1-inch diameter cylinder. In step 5, once we're done with printing, the print verification will be downlinked to the ground station via S-band, and then our assembly method is performed in step 6. If you look at step 6A and 6B above the mission timeline, you can see how our assembly method is performed by using a laser to fuse the 2 objects together. Once the assembly is done, the assembly is moved out of the chassis and secured for the next iteration of prints. And step 7 shows our next iteration of prints and our stretch goals, including a tall cylindrical print, an increased thickness cylindrical print, and a square structure. And then in 2030, the spacecraft will deorbit. Next slide, please.
Our additive manufacturing technology was selected via trade study. Our preliminary research identified 4 main candidates for this study. These include material extrusion, laser and electron beam directed energy deposition, as well as directed acoustic energy deposition. Following our trade study, we found that DAED was the optimal choice for our payload. This is because of its low power requirements, as well as its high research value. All of these systems were weighted based on their power, volume, mass, and requirements and their research value to our mission. We also performed a trade study to determine the optimal feedstock to use with this. We selected aluminum 6061. Next slide, please. So DAED is a highly experimental additive manufacturing technology. This process involves depositing a wire feedstock, usually metal, into a build area, at which point the deposition tool head compresses this into a voxel or a 3D pixel on your build space. This compression is assisted with acoustoplastic softening, done by vibrating the deposition head at a specified frequency. Research on aluminum 6061 in this process provides the following deposition parameters, including a vibrational amplitude of the tool head of 1.1 micrometers, and a nominal shear frequency of 60 kilohertz, and our nominal compression loads required for this process is only 100 newtons. DAED is special compared to the other candidates that we looked at for a trade study because it's a solid-state additive manufacturing process. This means that the material used in it does not need to be heated to the point of fusion, which is unique among these additive manufacturing processes, especially metal ones that usually require you to fuse metal. This process only requires you to raise the temperature of the feedstock to about 60 to 90% of the temperature required to fuse it. Next slide, please. So our mission success criteria can be organized into a flowchart. Starting with system initialization, we start with our additive manufacturing system, attempting to deposit one voxel layer cylinder onto the build plate, our build substrates. After this is achieved, our system will attempt to print a 3-inch high cylinder to be used by our laser welding system. The assembly system will take the finished part and attempt to weld these parts together. And the optimal success condition for our assembly system is to demonstrate repeated assembly. If our additive manufacturing system cannot or fails to print a 3-inch high specimen, we will have prefabricated specimens on board the payload to be used by the assembly system. If we meet these success conditions, we have stretch goals, including printing additional shapes with different parameters, and also testing the weld strength of our assembly system. Next slide, please.
Here we have a highlighted and color-coded depiction of the key systems within our payload. We've highlighted systems for both our selected ISAM capabilities, such as our DAED printing mechanism and our laser welder for assembly, as well as supporting subsystems such as our NDE computers for finished part analysis, as well as our power management system. Next slide, please. These are a few key components for our DAED printing system. We begin with our filament spool in the top left, which feeds aluminum 6061 filament into our wire feeder, which is then directed into our deposition head, where the printing process can begin on our consumable substrates. These substrates are located on a rotating build plate, and the remaining substrates are stored beneath the build plate, which is not pictured. Also not pictured in this diagram are the print graveyard that we are using in case of a failed print, or the prefabricated samples that enable assembly testing if deposition should fail. Next slide, please. Here we have a ConOps specifically for our payload operations. Here we detail the process from releasing from launch configurations in step 1 to beginning our manufacturing process with steps 2 through 5, and then going into our assembly process in steps 6 and 7. We will detail these steps more thoroughly with animations in the upcoming slides. Next slide, please.
So here we show our system block diagram, which is comprised of 4 major blocks. Those are thermal, power, command and data handling, as well as our fabrication system, which includes the NDE system. One thing to highlight is power is showcased in red. And like we said, the solar panels deliver 444 watts, but only 60 of that is delivered to the payload, which is delivered straight to our augmented batteries. We have 7 extra batteries that are handled by the PMAD, which is our power management and distribution computer. Another thing to note is that all analog and digital data goes through our core computer, which is a Sirius Leon 3FT computer. And that will establish a system state and then determine next steps and send updates to ground stations. Next slide, please. Here we'll show our additive manufacturing system with a short animation. So first, the system is raised up and a print flap is lowered. It secures a substrate, one of 12 substrates from the substrate storage system. The print locking flap redeploys. Then the printing gantry lowers. As shown here, the filament reel and the wire feeder are moved by 2 separate motors to ensure that the wire does not break. Down below, we have our transducer, which vibrates at 60 kilohertz, and shown in red is our nozzle head. As the system works, it deposits wire at about 0.4 millimeters per second, and then that 60 kilohertz is applied, which plasticizes the material and binds into the substrate. This is a little bit choppy, but it's showing a 3-day print, which is about a 3-inch print. It takes about 5 hours per inch to print, and then about 17 to 19 hours to recharge our batteries. And then as you can see, it is lifted up to the top of the satellite where it is secured at the top rotating bed. Next slide, please. Next, we show the assembly process. So here we show a new finished print. It will be raised up to the top of the satellite, and it slots into the bottom of the substrate of the previous print. Then a laser, which is a QCW or quasi-continuous wave laser,
will weld the seam between the two as both beds rotate. We're estimating this is going to be about a 2-minute long weld, which will take about 10% of our battery capacity. And that's factoring in about 70% of the energy being wasted through reflection on the aluminum. And then as you can see, it pushes the product through so that it can continue with the next sprint. Next slide, please. Here we show our non-destructive evaluation system. So we have 2 optical RDCam optical cameras. Note that there will not be any light in the satellite. There are components removed for clarity. So we will have LEDs that show, that let the optical cameras work. We have 1 FLIR boson camera as well in the middle there. And they will, as each voxel is printed, they verify print integrity. And if not, if the AI system determines there's not integrity, then it will do a full 3D scan of the product and then send that information down to determine next steps.
Now, destructive evaluation system is a real-time, fully autonomous, AI-based control and monitoring system. The traditional methods for NDE that has been used for space industry are ultrasound or thermography. However, those methods require a high cost of instruments, and they have relatively low performance compared to the commercial products. After conducting research, our team decided that image-based and the thermal-based machine learning process for the our system method. The commercial AI computer was chosen because of its high performance of the 21 tera operation per second, and its lower cost compared to the traditional space industry computer. Based on our SDK analysis of accumulated ionizing dose, for the 45 degrees of inclination, 2 years of mission duration in low Earth orbit, at least 2 millimeter of the aluminum thickness of the aluminum radiation shielding will be used to prevent single event effect. In addition to the convolutional neural network, transfer learning is adapted to increase the speed of the machine learning training speed, machine learning training process, also reinforce the machine learning technique, especially for the defects classification. According to the historical research of the transfer learning with the CNNs, 512 megabytes of the VGG16 model, pre-trained model, achieves the 94.7% of the accuracy of defect detections. Next slide. Once our ND system detects the defects, based on the top and side cameras, failed printed parts are managed by the Hacker Motion Details track system with the 8 storage slots. As you can see on the left image, 2 slots are pre-filled, and they will be used for assembly demonstration in case our printing system fails. As shown in the video on the right side, failed printed parts or square-shaped printed parts that need to be stored are managed by or secured by a small arm mounting to the printing entry. Next slide, please. This is our high-level commanded data handling concept operation. In nominal stages of satellites downlink the data, including batteries percentages, ND's status, and the diagnostic data is received from each subsystems. Normally, our system is designed to be fully autonomous. So our core computer and ND system detects the defect and then manage the defect or manage the faults autonomously. However, if the faulty level reaches the really high, and if the whole FDIR system is failed, that's the moment that when the human intervention from the ground station will be occurred, as you can see in the red color of the arrow. It will uplink the comments or override the comments to restart the faulty system to recover to the nominal stages. Next slide, please.
So for our power budget, we base our power budget on the power draw, the growth percentage, and the duty cycle for each electronic component within 9 separate subsystems. The table on the left shows the total power draw for each subsystem during 4 different modes of operation. And in order to meet the large power draw for these modes, we included 7 additional 2P8S battery module, lithium-ion battery modules provided by Blue Canyon Technologies. The graph on the right shows the charging cycle for a 3-inch print. And the blue lines on the graph represent printing time. The orange lines represent bed heating, and the gray lines represent idle or charging time. Each print cycle takes around 6 hours, and each charge cycle takes around 20 hours, as previously stated. Next slide, please. So for our thermal systems on board the payload, we have a passive cooling system and an active cooling system. The passive cooling system uses 12 wall-mounted MISER radiator panels, which can dissipate about 12 watts per panel. The passive system is used primarily for the heated print substrates, which you can see the internals of, which includes a patch heater sandwiched between two subcomponents, as well as the D.A.E.D. system. The active cooling system is going to use Novex 7000 engineering fluid in a fluid loop connected to two UAM radiator panels with fluid paths embedded. This system will be used to cool the onboard avionics systems and the assembly laser chassis. Next slide, please. For our launch considerations, we plan to use a rideshare mission with a SpaceX Falcon 9, and so our payload structures were specifically designed to survive the expected loads of that launch. Detailed engineering drawing of our chassis can be seen in the top right, and this chassis was used for random vibration FEA simulations. The results of these simulations can be seen in the bottom three images, which include random vibration in the X, Y, and Z directions. And it includes a 3 sigma scaling factor in order to more easily convey the visual results. Our structure was found to withstand the expected loads, and we verified this with direct stiffness method hand calculations. The animation on the bottom displays a cross-headed mounting system for components that move freely during operation, and this will be used in place during launch in order to secure these systems.
Next slide, please. So here you can see the overall mission and payload material cost estimates. The mission cost is calculated considering the cost categories listed in the first table. By calculating non-recurring and recurring production costs, we were able to estimate the mission cost to be $50.4 million. These calculations were made based on NASA standards. So for universal level projects, the cost would highly decrease. To calculate the payload material cost, we considered each component needed for the subsystems listed on the second table, and as you can see, the total payload cost is estimated to be $715,000. Next slide, please. Here you can see the mass budget for this project. The growth allowance is calculated based on the AIAA standards, and the total system mass is 69.8 kilograms. The table below outlines the allowable mass and mass limit for this project, along with the mass margin for each based on a total system mass. This concludes that we are within the mass requirement and still have additional capacity available if further components need to be integrated. Displayed on the right is the mass versus time plot, showing how the system mass changes throughout the different phases of this mission. Next slide, please. Several mission risks were identified for Project H.A.D.E.S. These include system risks that apply to the total payload, project risks that apply to the program and its management, and risks specific to additive manufacturing and its fabrication system. Each risk's formal statements are listed in the center column with its corresponding mitigation strategies in the rightmost column. One of the key risks we identified is the feedstock breakage. If the element filament is damaged, the system is unable to deposit any material, which can cause mission failure. To prevent this, we will utilize a pin roller system that will control the speed of spooling into the deposition head. Next slide, please.
Project H.A.D.E.S is currently estimated to be in Phase A of the mission timeline based on NASA NEH robotic mission project and program lifecycle estimation tools. This schedule allocates 2 years for further research and development of our systems, along with an additional 2 years after that for integration, testing, and assembly of our final engineering and flight models. This would lead up to our launch in 2030. Our team presented a system requirements review in the fall of last year and a conceptual design review to our industry and faculty advisors this spring. The teams identified the systems engineering steps we need to move forward from here to further gain to our path to PDR. We need to further outline our systems engineering management plan and evaluate further program requirements, cost, and schedule, along with establishing validation plans for our payload subsystems and how we intend to test them for our final models. Next slide, please. Lots of our test and manufacturing work has to be done specifically in regard to our DAED additive manufacturing system, as nothing has ever been flown similar to that before. Multiple individual components need to have environmental and vibrational testing done for them, since these are a lot of off-the-shelf parts. Some of them already have flight heritage, others do not, and we need to focus on the ones that do not. From there, we might need to make modifications to some of these off-the-shelf parts in order to validate that they can qualify and meet our launch and space rating requirements. From there, we will optimize our design for assembly to ensure that this could feasibly be assembled by a team of people. And for the last section of this, on that finalized assembled system, will be to train and test our AI failure detection and handling model on a 1-to-1 scale of the version that will fly in space in order to ensure its effectiveness. Next slide, please. In terms of our technological gaps, the primary gap is our DAED additive manufacturing system specifics. Lots of its aspects have never been tested before in microgravity, and that is one of our primary concerns and something we would like to investigate further. Another important one is our software optimization. AI models tend to be very power and computationally hungry, and this has never been optimized in the way that we're looking to do it before. So we will do our best to take a model built for a ground-based system and translate it into the thermal, computational, and power constraints of a small satellite mission like Project H.A.D.E.S. Next slide, please.
You guys have just 1 minute, so you might want to just hit the rest of these really quickly.
Okay, I can hit these quickly. So we experienced a number of challenges throughout our design, and they started with narrowing our scope from ISAM to a few capabilities. ISAM is a large field, and there are many paths our design was considered in. The next challenge was working with the BCT class bus, which we found it difficult to find technical specifications, and eventually finding only 60 watts of payload power meant redesign and rework. And eventually settling on a design that balanced innovation and feasibility was difficult, as our earlier designs weren't feasible with those power requirements. Next slide. We believe our design offers a lot of research value while balancing timeline, cost, power, mass, structural, and thermal considerations. It displays multiple key ISAM capabilities and is a good launching off point for the future of orbital manufacturing. It will be essential to the new space age as we build new large structures and new large vehicles. Project H.A.D.E.S has the potential to define humanity's future in this space and set the scene for expansion into the outer solar system. Next slide, please. The mission plan we've shown provides a solid proof of concept for a system with repeatable structural elements. The data we will collect will be essential to inform future missions.
Okay, guys, we're gonna have to wrap it. So just if you have any more slides, just put them up for 5 seconds each.
This is the last slide. Yeah. So for your consideration, Project H.A.D.E.S.
Good job, guys.
Do you have any
Okay.
questions now?
We have time for questions, so if the judges have questions, just come off mute and ask.
We have one here.
Could you go back to the print evaluation slide?
Slide 17.
No, slide 17. Slide 17. Yeah, so I was just wondering, so you mentioned using a convolutional neural network. So the inputs would be the outputs of these two types of cameras you guys have?
Yes, and also we will have a pre-trained model that has
on the ground.
made on the ground.
And you do the reference. And And then I'm wondering though, I don't know if any Jetson devices that are like radiation hardened to be used in space. I was wondering the GPU considerations there. I don't think there are many options actually, so it's fine for that as a placeholder. But if you looked into any like actual radiation hardened like compute that you could use.
So this computer is actually a commercial.
So this is actually a commercial off-the-shelf computer. It is not technically radiation hardened. That's why we conducted our research of SDK analysis of total analyzing tons to estimate the minimum thickness of the radiation shielding will be required for our commercial computers. We also had a 2 millimeter is the minimum thickness that we estimated.
Are there any more questions?
Yes, I have a question, Vinego. Yeah. If you can go to your trade studies charts, I wasn't clear about your trades.
Which trade? The additive manufacturing one?
Well, it wasn't clear if the trades were more about what project you wanted to do versus you wanted to accomplish a mission of some kind, and then you study a different trades to see how you accomplish the mission. So that's the part I was getting confused. You don't mind going to a trade slide where you show them?
Slide it is?
Probably slide somewhere between 11 and 13, I think. Nope. Before that, sorry.
I think it was earlier on.
Slide 8.
I noted an earlier slide. It was like
Slide 8.
7, 8, yeah, 8.
All right. What was the question?
I'm not sure what your trades were. Is this your trade chart?
Yeah, that's the trade study for the additive manufacturing system.
Okay, okay. Okay, that makes more sense. Sorry, I was not clear about that. Thank you.
No problem. Any other questions?
I do have a comment. I really like your CAD animations. Very impressive. What software did you use for that?
All of that, we did most of our actual structures in CAD, and then we imported them into Blender. And we did all
Into what? Sorry.
CAD software, but Blender was animations. Thank you.
Okay. All right. I think that is time. Great work. Let's hear it from Team H.A.D.E.S. And then you guys, you can assemble for your photo while the judges take time to record the scores. We got a little behind here, so why don't we regroup? Why don't we regroup and we'll say the next team will start at 50 past the hour.
I want to see everyone's heads though. Everyone's head.
Okay.
Well, no, well, we can't have one person kneeling. You gotta come up to the front. All right. Yeah, that works better. There we go. There we go. Okay, ready? 1, 2. Oh my gosh. That's fine. Very good. 1 more. Okay. Perfect. Thank you.
Thank you.
Great job, guys. I'm gonna mute on our end, so.
Okay, the next team, I think is this our first remote team for the day? We're gonna start at 11:50. It is. Next up is Team Aces, another team from Penn State. So you guys, or yeah, we can pull up their slides. You guys can if you have a camera, you can put it on, and then just be ready to go. We'll start at 11:50 or maybe just a minute before. Do you guys need to share your slides locally? I mean, on your computer, or are you okay with us sharing them?
We might be better if we share, actually, so that we can press. No.
Okay, is it you, Malik, who would be sharing?
Yeah.
Okay. Rachel, if you can make him host and let them share.
You shouldn't need to be a co-host to share.
Oh, okay. Yeah.
Okay.
Found it. There you go.
And then if I.
Okay. We're 11:49. I think that's close enough. Why don't you guys get started?
Hey, hello, everyone. We are Team Autonomous Concentrated Energy Solutions, or ACES. So this is our watchdog project. Today we have, I'm Malik, we have Joseph, Kiara, and George presenting with us today. So basically there's a need to get rid of microdebris in space because it creates impacts on satellites and lowers their lifespan. So for our solution, we're using a laser to ablate the microdebris and move it around. So that is basically our mission. So I am the project manager. With us, in addition to the team, we have Joe, who is our astrodynamics lead. We have Kiara on CAD, George on the power, and Claire and Denver on command and data handling and ground systems. And Nick was our, he graduated early, but he was our citations and project scoping. So early in the semester, the project began in the fall. Then we picked a project manager. We chose our capabilities. We did, later on, we did top level requirements and focused on ConOps. Then we did a trait study to pick a certain ConOp that we proceeded with. Then later on, we had the midpoint showcase. In the spring, we looked at our initial analysis plan. And then we focused on the subsystem decomposition, and finally we established this. Eventually, we established this presentation. Okay, so looking at the background, essentially microdebris is projected to grow exponentially, especially in LEO orbit. This has a huge impact on ISAM because it, as you can see on the table on the top right, it has a very large increase in the cost and a decrease in the lifespan of satellites. And this is especially true for even small microdebris particles, because even for 5 centimeters, it's like being hit by a bus. So our ablation laser was inspired by different optical power transmission systems that already exist, such as the US AFRL ground-based laser, or just typical concentrated solar energy devices. So we also looked at just other existing literature on laser ablation for moving debris. So overall, our mission statement consists of using optical power transmission to essentially move microdebris particles and deorbit them to satisfy the ISAM initiative for defense against microdebris. And we will be doing this with our 3 operations that consist of acquiring, tracking, and monitoring these microdebris particles, reorienting our devices to do this, and finally delivering this optical power. So initially we looked at 3 different potential concepts of operations. The first one was essentially using a unfolding lens. The second one was using a flexible lens so that you can change the focus and increase the efficiency. And third, we looked at a solar pump laser. However, after doing trait studies, we picked the solar pump laser because it was basically the most efficient way. However, we realized that a solar pumped laser is very technically difficult to implement. So we instead focused on just using capacitors and a basic laser to do laser ablation.
Okay, so now I'll move into the storyboard of our operations. So on here is the macro level mission architecture. Starting on the left in step 1, we launch from the Minotaur 4 rocket into stage 2, where we will deploy in our target orbit, and the orbital parameters you can see are in the bottom left there. After we're at this point, we'll be charging the batteries on the bus. At this stage, we will be relaying information about the location of debris particles to our payload or to our bus, to which it will autonomously move to a waypoint location where it expects to have high encounters with debris. Finally, demonstrating their first operation, the payload will wait until it encounters a debris particle and detects this with its tracking abilities. And then once it finds this target, determines its trajectory, it will use pulse laser ablation in order to move it onto a suborbital trajectory, satisfying operations 2 and 3. And then after this stage, the spacecraft will deorbit after about 5 years of operation. Expanding on that 5th step on the last slide, some of our orbital procedures will be to do a series of Hammond transfers in order to reach these locations, which we dub the waypoint location. So you can see in the figure above, that's just showing sort of visually how the altitudes of the orbits change. So initially it's on that green orbit. In this example case, currently we're lagging the waypoint location. So the satellite will move onto a lower trajectory such that it can catch up with that location. And then it'll do a final Hammond transfer just to reach the target. And over the span of the mission, we're figuring we'll be doing this 4 total times, as you can see on the Delta V budget there. And then also we have just some end-of-life deorbit Delta V and some for attitude adjustment as well. And then next here is kind of a closer view of our payload and showing off some of the operations it will do. Once it's in space, there is a boom on board that will deploy to allow our long-range LiDAR to have a better field of view. Along with this, we have a galvanometer, which will be directing the laser as it's generated towards our debris particle. Once it's fully deployed, it will wait until it encounters a debris particle, which will be detected by that LiDAR. The target will be confirmed using the IR camera, which is sort of recessed in the back there. Once these operations happen, our supercapacitor, after it had been charged, will dump its power to the laser so that we can ablate a particle over a short span during an encounter.
So first, the 92-inch Minotaur fairing detaches in halves along with a damping and separation system. You can see our dual configuration solar panels coming in there. The payload is attached to the outside of the bus with an Esper ring, and it's zooming in onto our payload. The first thing that happens is our boom extends to about 3 times the length of the 27-inch payload. Our LiDAR spins and detects debris. Our IR camera confirms this, and the red dots that represent the lasers go through the galvanometer and are reflected by mirrors to get to where they need to go. We have slight technical difficulties. On the bottom left, we have our 3 view of the payload. You can see all of the labeled components of our payload and where they belong inside of the box. In the top right, we have our bill of materials that just lists all of these things. And in the bottom right, we have our payload mass budget. You can see with a 20% margin, our total payload mass in kilograms is 65.4.
Okay, so essentially to pick an ideal laser and a tracking monitor, we did trade studies. And so the first trade study begins here with essentially we looked at over 300 different industrial laser models, and we plotted them against their mass and the largest dimension that they have, yes, their average power and peak power. And basically this just helps us look at what we can achieve as like the feasible current bounds for these lasers. And hopefully in the future, if we are able to find how laser ablation impacts of the orbit time, we can choose one of these lasers, and or we can look at the trends here and see if that fits within our bounds. So from this, we realized that a case study laser that we picked is the Flare NX. So it's a very small 2 kilogram laser. However, it can do UV light, which is very high absorption for aluminum, ensuring ablation. And it's a pulse laser, which is similar to what we're implementing. So another thing that we looked at for the tracker itself is we looked at the catcher's mid-final report, and we realized from this that to ensure the most encounters in our LiDAR system, we want to see between a 10-kilometer and 100-kilometer LiDAR, so that we basically sweep around 10,000 microdebris particles that are 5 centimeter in 1 year. So doing a trade study on the tracker itself, we found that using a LiDAR is the best decision because it's the most precise and the longest range that we can get besides the radar. The reason that we did not choose the radar is because we realized that we can use a ground laser to find clouds of microdebris instead. To help the LiDAR, we're using an infrared camera to essentially detect the scattering that occurs. This is comparable to the ISAT-2, which uses a telescope to detect the scattering, and it ensures very high precision and long range.
So to begin with thermal, the task was to find initially what the time in the sun would be, which is what you can see on the right there in the top graph. So it gives us what our sun times is, and therefore what the heat load from the sun will be. Adding that to the internal heat load generated, we get about 353 watts. Our payload is going to have one open side directly into space, which is where the boom is extending from, and then louvers on 2 of the other sides, giving us a combined radiating area of about 0.78 square meters. This passive cooling alone allows us to get down to about 38 degrees Celsius. And if we incorporate about 75 watts of active cooling, we can get that to a more ideal operating temperature of about 20 degrees Celsius. After that, the task was to look like during eclipse. So the payload won't be active during eclipse. So the only internal heat generation will come from active heating. It was found that the payload's going to get down to roughly minus 73 Celsius. And we want to be at a more sustainable 15 degrees Celsius. So this requires about 59.81 watts of active heating, as you can see where it intersects on the graph over there. After that, I was looking at the power subsystem, and because of the nature of the laser and the LiDAR and everything, we were going to need some pretty good battery modules. So there was a company named Eagle Picture Technologies that makes space-rated lithium-ion batteries. Using 8 of these in a battery module configuration, you can see the specs for that at the right, along with the supercapacitor bank comprised of 12 supercapacitors. And the batteries use a DC-DC boost converter to discharge all of their, not all of their energy, but discharge energy to charge the supercapacitors, which can then be discharged to fire the laser itself. The laser is going to be activated for about 60 seconds at a time of continuous pulse fire before needing recharge. That gives us plenty of time for laser ablation. With how much the LiDAR consumes, which is about 1,000 watts, with losses 1,111 watt hours. That, in addition to the other IR cameras, supercapacitors, cooling, etc., and the payload, you can see that it consumes about 60% of the battery's energy during operation, leaving about 40% for the bus, which is more than enough since the only bus operations are going to be maybe propulsion and gyros.
Okay, now moving into some of the physical simulations that we did for the payload's operation. So here's sort of an overview of the methodology we used to test this out. This is a figure kind of showing how we set this up in MATLAB to simulate how forcing a particle in space would change its trajectory. So starting on the right, basically we have the watchdog payload and a debris particle in a pretty much randomized orbit, or the debris is slightly randomized compared to the watchdog. to allow for a close encounter to happen. So over the course of this time, the orbits are propagated over a time span, and this is using basically just normal point mass propagations. Once a certain threshold is reached between the separation distance of the watchdog and the debris, say less than 5 kilometers, for example, it will switch to doing a numerical propagation of the equations of motion, and within MATLAB you'll see soon is using ODE 45, and this ablation force is added onto the debris, and this force is a function of essentially the distance between, or it's a function of the ablation rate as well as the direction between the watchdog and the debris. So this force will be applied over this duration, which may be 40 or 60 seconds long. After this close approach ends, the final conditions of that approach are used as new initial conditions for a normal propagation, and then we can use that to essentially see what the altered path approximately is. So on the next slide here, this shows the output of this simulation. So starting at step 1, essentially the simulation begins. In this case, we're pretty much in our target orbit, and the debris is in the same orbital elements, except that it's slightly lower in the orbit, so the semi-major axis is a little bit less. The debris is lagging the satellite by about 10 kilometers. About a third of the way through this orbit, a close approach occurs, and this happens when their separation is less than 5 kilometers, which the figure on the left is pretty much just zoomed in on the figure of the right, showing pretty much where this occurs and for the duration of the orbit. This lasts about 40 seconds, and the force of ablation is applied onto the particle. Very faintly, you can see that the trajectory does change slightly. And then after this stage, looking on the basically step 3 of the right figure, you can see the debris path is altered, and then coming around to the other side, practically where it started. Once the altitude is less than 100 kilometers in our simulation, we essentially deem the debris particle is successfully deorbited. Okay. So now moving on, here's some of the risks that we considered. These are just some of the most prominent risks we thought of with Watchdog. So the first is lasering a non-debris target. If we didn't have sufficient checking, the payload could laser objects that aren't debris, such as another satellite, which we wouldn't want to have happen. So we mitigated this risk by including an IR camera that's capable of distinguishing between the debris and some of the other objects. The second was pushing debris in trajectories that weren't suborbital. If we were to ablate any particle that we found, we might be pushing it with its velocity vector, for example, which wouldn't be assisting in deorbiting it. It would actually be boosting its orbit. So the tracking system has to verify first that the trajectory is against, or the laser ablation force is against the velocity vector, so that this doesn't happen. This isn't like a totally eliminated risk, though, because there's the possibility that we may ablate the particle some, but not completely deorbit it. Next is some regulatory risks. Some parties might not be comfortable with having a debris clearing satellite near other operational satellites. So to mitigate this, we're going to communicate with other satellite hosts that are near the operating orbit of Watchdog to make sure there's no conflictions. And if there are, we'll just move the payload into a different orbit. Here's some more expansion on some of the risks, just some of the costs that we spec'd out. So using the SCM19 software, we factored into some of the unit costs of the subsystems on the bus to handle some of the things that are going on the payload. We did identify that some of the things we're using, such as the laser, the tracker, and some thermal systems, may be low on TRL, likely around 3 or 4. So we may need some preceding missions to boost this, but to account for that on the mission, we put some overhead on the power, ADCS, command and data handling, and thermal systems. We added 100% there. Mainly the methodology there is the TRL needs to nearly double, so we'll essentially double the high cost there. So that makes the mean cost around 51.7 million, where the high would be 77.8. And again, this is just for the unit costs of objects on the payload or on the satellite. Next is our data handling and comms. So we'll be using 3 ground stations. Mentioned previously that we had 1 ground station that's basically telling the satellite where there are high debris concentrations. So we'll be using the Space Fence radar located in the Marshall Islands. An important caveat is it's not used for communications. It's solely a radar that's used to call out where these debris particles are. The other two we'll be using is the Malabar Transmitter Annex in the Cape, and then the other is the Aurora Ground Station in New Zealand, which these are both on the S-band transmission range. And using some analysis in STK, we found that about 12 times per day, we get access for an average about 12 minutes. Moving on from this, we also did some uplink and downlink budgets. So we have margins that you can see highlighted below. The communication system we're thinking of using is on the S-band frequency, an all-metal patch antenna that's provided by Blue Canyon. We also did some SDK analysis to look at some of the access times we had, as I mentioned in the last slide. We estimated that a high end of the range of the data transmitted would be about 100 megabytes. So we were able to determine that the data rate would be about 12.1 megabits per second, which we used within this budget. And then this is just a flow diagram showing how the data would flow between the computers within the payload and the bus. We would have a separate CPU for the command data handling on the bus, on the payload, while on the bus we would have one for command and data handling and the other for GNC handling their respective subsystems there. And then this is just some of the biggest challenges we encountered during the project. We had a technical challenge proving that debris could be pushed in the desired trajectories. We solved this essentially humored this essentially by making it the orbital MATLAB simulation that you saw before, essentially to show the effect of how the payload would react with a debris encounter. The second was a technical challenge, developing a laser system that could be pumped by solar light. One of our initial ideas was to use solar light essentially to create our laser beam or power our laser. But essentially this idea was avoided to avoid complexity and feasibility risks. So going on to the third challenge, we had a technical challenge of modeling ablation for the particle. What we had wanted to do is basically do our own simulations in order to find out how we could change the trajectory of the debris, or how we could figure out how much mass was coming off of a particle so we get momentum change characteristics. But that would have been a bit too much work for us in the time span that we had. So we settled for using a paper that had a certain case with certain different parameters and the ablation results from that to drive basically the analysis. And then finally, some of the technology gaps. As I mentioned before, the laser target tracker and thermal management are some of the lower TRL items within our payload. As for the laser system, our power output might need to be on the scale of kilowatts. So there hasn't really been much demonstrated in space on that scale, at least for this use case. So that's sort of a gap there. The target tracker itself, we found that LiDAR would be the most suitable, as we mentioned before, although it would only be feasible if it was very accurate to several kilometers, which we're not exactly certain of. Finally, the laser thermal system. Some of the more ideal options to use would be something that uses a pumping medium. Most lasers used in the lab would have some kind of chiller that has some kind of fluid that would be pumped through, but that hasn't been demonstrated much, at least to our knowledge in space. Then also we have a paper that we submitted for the project. It's an 18-page paper in AIAA formatting, and would be intended to be submitted to SciTech. And then the abstract length and references are there below.
While our propulsion, power, and thermal subsystems have design verification work, our structural and communications and data handling systems need more work and information to develop a GNC model, perform load analysis, and finalize the size and power of onboard computers. Next slide. We also need to enhance our astrodynamics model to include the power and forces needed to move debris, create laser ablation simulations, choose or design a capable laser for our requirements, and do lab demos for the laser and tracker. And for our lessons learned, the first and third points kind of go together. At the start, we would have liked to be more knowledgeable about the technology available to us before getting into advanced planning so that we can avoid issues like having a really difficult or impossible mission. And the second point is to have a good time to task balance so that we don't spend too much time on one thing while neglecting others. Our Watchdog mission aims to raise awareness for the worsening problem of microdebris in low Earth orbit. As a successful mission, it would boost research for lasers and tracking technology, since the mission's goal of ablating small debris from a far distance is, of course, innovative in nature. And that concludes our presentation. We would love to answer any questions.
Okay, if the judges have any questions, you guys can come off mute. Or if you're in the room, yeah, if you're in the room, then you can probably find a microphone.
I have one. I think you have some good forward work identified. I was just wondering, with the high power requirements for the laser, is the bus suitable for generating that power and recharging the batteries and for pointing control? Have you done any analysis on that?
So George will be answering that, but we were using a capacitor system. So yeah.
And what we have, like the batteries that are being used can charge, I think it was from 0 charge, it would take 5 hours to fully charge the battery module, but we're assuming that the batteries are going to be fully charged before getting into orbit. And then the supercapacitors can be charged in about 20 minutes, and it's a 12 supercapacitor bank. That can be discharged for about 60 seconds to provide ample enough power to fire our laser. And the size configuration of the batteries they weren't very large, so they fit into the bus quite well.
Okay, are there other questions from the judges? So I'll ask one, and maybe you covered it. But when you blast something with a laser in orbit, there's always a risk of creating more debris. Like how do you balance the desire to eliminate some debris while with the risk of creating more in the process?
So we we were looking at like simulations to see how much spatter and so on forms when we ablate it, but unfortunately, it's very hard to run these simulations because like they're very computationally expensive. So we basically had a bottleneck there, and we were just like looking at like that's in our future work to understand basically. But one of the ideas we had was if we keep like iteratively scanning the region where the microdebris is, we can the lidar will reflect light or reflect light, sorry, when it hits the separated like if the particle breaks into like two, for example, it will the lidar will be able to reflect light off of the second one, so we can essentially track the newer particles that form. But the goal is not to basically like split it up. It's to ablate it and like push it into deorbiting. Does that answer your question?
Yeah, and just to follow up, is there an experiment you could do without going into orbit that where you could test to see that whether that is viable?
Yeah, of course. So we could just do it in like a vacuum, and we can use. I mean, there are a lot of like industrial lasers where we could test like what happens upon even like a small particle of aluminum or just like a plate of aluminum, and see how much I guess breakage of material there is from the like wall or plate or particle that we do on Earth, and basically tuning our laser parameters such that it minimizes this, and then we can apply it in space. However, it wasn't in our scope. We don't have industrial lasers, unfortunately.
Now, Understood. It's more like identifying the next steps because I see that as a key next step before you go to like a PDR is like, okay, does this really work? I think we have time for one more question.
And I was going to ask along the similar lines. It didn't sound like you established the minimum, I don't know what the right term is, fluence to create the ablation itself. And so I was concerned about spot size and fluence levels. Do you know how much you need to actually initiate ablation rather than just have light hit it and reflect off? Over.
So the laser we chose like as a case study, which is a Flare NX, so we ran some like very basic back of the envelope calculations and it showed around like 24 hours to deorbit. I mean, of course, this is a very long amount of time, but also like this laser is very small. Like we chose basically the smallest laser that we possibly can. So we're hoping that based on our laser trade study, if I go back to the slide here, yeah, like we can essentially pick we can look at these trends and we can pick a laser that fits within these bounds, like the mass constraint and the largest dimension constraint. And we can try to extrapolate, or we can see what the physical modern bounds are. And we believe that at least there is like a optimal point where there exists a laser that is strong enough to ablate the microdebris, causing it to deorbit. Is that
okay? I think we've essentially run out of time. I know we're going to the break, and given that, I think we're already at least 5 minutes behind schedule and probably a couple more minutes here. I think why don't we push it back 10 minutes? So we'll return at 12:40 Pacific, 3:40 Eastern for GatorChomp. But yeah, if we thank the team, we can do your microphone or otherwise.
I think we're fine in the room if we want to start at 3:30. Online, if you guys are okay with that, I think we'd be okay.
Okay, judges, you're okay to pick it back up at 3:30?
Can I have 3:35? I'm trying to do all of my scoring in this break.
Yeah.
Sorry, Russ.
All right.
Okay, 3:35.
3:35. Okay, it's agreed. Thank you. We'll see you in 15 minutes. Okay, we're going to start in just about 2 minutes, exactly 2 minutes here, with GatorChomp. So, Rachel, if you can pull up their slides, I believe they are in the room in Goddard, and we'll get started right at 3:35 sharp. And of course, you have to turn your microphone back on at Goddard.
Okay, we're gonna get ready in here. Maybe, wait, another. I'll tell you when to start, okay? Don't hold it too close. A little, you'll have to speak a little louder, just a little bit. Okay, you're probably good to start.
Hey everyone, my name is Jonathan Tyndall, and today I'll be presenting with Jake Piccarello for GatorChomp. We are part of the University of Florida, and we're presenting our project called Gator Arms. Next slide, please. So current space robotic systems are too complex, they're large, they're expensive, and single mission focused for use in small sat ISAM missions. So to fix this, we propose a small scale autonomous twin robotic arm system with interchangeable end effectors for ISAM capabilities. So the two arms will have multiple different tools that can be swapped out and will enable complex and precise ISAM capabilities. The small scale nature of the design reduces cost, it reduces mass, volume, power requirements, and expands the potential user base to a whole new range of clientele. The current status is tier L2 to 3. We've started developing prototypes and will continue to do so over the summer. Our project was started for Cosmic, but will not end for Cosmic. We submitted an abstract that was accepted at the Utah State SmallSat Conference. We also submitted a proposal for the NASA Tech League competition that will, if accepted, will give us $500,000 in orbital flights. So if you guys want to see on the right, this is the Gator arms. We have 2 twin robotic arms on both sides, and we also have a tool holder down at the bottom that can hold 10 different total tools. So the idea is that these arms will come in, be able to swap out different tools with a proprietary interchangeable end effector design. To get a scale of, get a scale for reference, they're about the length of my arm right here. So they're much smaller than anything else currently existing. So can I get a next slide, please? Something else I did want to mention before is our original inspiration for this project was, what if we could solve a Rubik's Cube in space? That'd be kind of cool, right? I don't know about you guys, but I can't solve a Rubik's Cube on Earth, so we knew it would be a challenge. But we are an 11-person team of MAE engineering students at UF. We are unique in that I think we're the only team that isn't a part of a final Capstone class. So we're doing this as a design team project. Next slide, please. So we started in late October when our team formed and our project manager was selected. I'm the project manager, I don't know why. In November, our operations and capabilities were chosen, and then we finished the year off with a system requirements review. Going into the next year, our trade studies were completed around February with a conceptual design review to our 2 professors, Dr. Christopher Peterson and Mr. Michael Generali, as well as Mr. Brian Nerfer, our NASA advisor. Finally, we developed a PDR and finalized a presentation in April, and now we're here. Next slide, please. So moving on to impacts. We focus on the small scale nature, mainly to support other prototype, other designs and
missions, but also to enable future servicing capabilities, such as replacing existing solar panels or being able to scan existing satellites. So for example, when we presented the Astro-Scale, our design for Gator arms, we emphasized our capability to have, say, a camera on one of the arms, to be able to go up to another satellite and to be able to scan around the satellite and take a bunch of 2D images and be able to create a 3D model of this satellite and find out where any potential damage is. And then we can swap out tools, right? And be able to fix wherever this damage or this leak is. So we're also trying to reduce the cost as much as possible. So instead of spending tens of millions of dollars on being able to, on a robotic arm, we could have it in the hundreds of thousands of dollars. So next slide, please. Moving on to feasibility, when we submitted our tech lead proposal, we had to submit it in a 8-month time range. So as we can see up here, this is a Gantt chart of our expected timeline. We expect to create a low fidelity model in about a semester, and then be able to, over the next around 6 months, be able to do 3 prototypes. First prototype would exit around TRL 5 and do TVAC testing, and then we've further developed TRL 6, and then TRL 4, excuse me, and then TRL 5. And then finally, we would have our final high fidelity model in around spring 2026. So basically, this is all to say that our plans are to develop this in a short time period and that it would be attainable by 2030. Moving on. So moving on to innovation, well, there's 3 main things. We are focusing on the smaller scale nature, so to be able to adapt to, for example, earlier today, Prometheus presented their presentation, and they were needing a robotic arm for their welder, but they didn't have one, so they ended up just scaling down an existing arm that was much larger and was not suited for the mission. We could solve that capability by, instead of scaling, which would not be able to be feasible in real life, we could do that. We could integrate with Prometheus and be able to build a space welder using our robotic arms. And we could also have the second robotic arm be used to hold on or clamp the material as well. So, and then, like I said earlier, Astro-Scale was very interested in our scanning technology, so focusing on in-orbit servicing, being able to fix existing satellites and extend their mission periods. Next slide. So the 3D autonomous operations that we are expecting to perform is visualizing and determining target object position, being able to interchange our tools for desired operations, so enabling more complex missions, and articulating the target object. So after we grab onto this object, we need to be able to secure it and so that it won't get away from us, and then performing the desired task in the object, whether that be drilling or scanning or being able to add a solar panel or whatever is necessary. We considered the extreme temperatures and conducted thermal analyses using SDK with a temperature range of -81.3 to 25.8 Celsius in orbit. We're going to utilize multi-layer insulation coating to help prevent thermal issues with any of our motors or with our processing software. Moving on. So our proposed design also meets the volume requirements of the VCT-X.Bus. We will use an NVIDIA Jetson Orin Nano for our processing, and it takes up a small part of our total space. Most of our space is taken up by our 7 motors in the arms itself. The twin arms and tool belt will fit inside the launch variant, so we use a SpaceX Falcon for our analysis. And then we performed a mass analysis that found that the total payload is well below the 70 kilogram payload limit. So a fully loaded payload with both arms, the end effectors, and the tool belt will be about 20.4 kilograms. The heaviest contributors were obviously the tool belt and 7 motors and solenoids. So overall, it fits within our volume and mass constraints. Moving on. So our processing is handled by the NVIDIA Jetson Orin Nano. Signals are sent from the computer to the NEMO 17 motors, and then each NEMO 17 motor has an encoder that will be able to tell the angle of the motor arms and be able to adjust as necessary. The peak power consumption amounts to about 339 watts. So the proposed bus provides enough power for the capabilities. Most of this is taken up by the 7 motors, obviously. And then a cost analysis was conducted, and it reports a total cost of $4,231 using just on-Earth materials and ideal manufacturing processes. Obviously, this number is not realistic at all, so I would multiply at least by a factor of 10 for it to be somewhat more accurate. But the point of including this number is that the total cost is going to be in around the hundreds of thousands rather than the tens of millions. So to enable more adoption of the technology. But next slide. So these are some of the sources we considered when we were developing our design. Again, including the robotic arms themselves. We used some sources from Utah State. But if you guys are more interested in some of the literature we reviewed and utilized, please see our paper. Next slide. Again, a big issue was the computation and radiation hardening. So we looked into that in depth in our paper. Next slide. So as NASA people know, there has been quite a lot of interest in robotic arms in space, mostly in OSAM-1, which is less talked about here because the technical sheets aren't as available. But another awesome project was DARPA's RSGS program, which is very similar to what we are doing, but it was for large-scale servicing of geosatellites. And it is a TRL-6, so it has yet to launch to space after years of delays, and is well over budget. So we're trying to come in and make these arms. We're using the same twin arm technology, but we are making them much smaller so that they can be used for CubeSats. As we've seen today, the robotic arm in the rock was actually initially on the RSGS program, so it was adapted for the same one. Another one is the GatorChomp inchworm robot, which has flown to space, but it's a single medium scale arm designed for ISAM, so still much larger than what we are. And if we go to the next slide, we can see our arms compared to the Gate AI arm. So they both feature 6 degrees of freedom, but the extended length is about 30 inches for our arms, so it's about half of the length of the Gate AI arms. So it's also a fraction of the weight, and most importantly, it is a fraction of the cost. Moving on. So this brings us to our risk. We use a standard NASA risk chart for our analyses. So moving on, we can see that the risks that we identified are most severe with criticality level 1 is the computer failure due to the or nano or a charging failure or a memory failure. We are concerned because obviously if we can't control where the arms are going, then the mission is lost. So we have abilities to reduce tool failure because we have multiple tools and redundancies in our arms. So those failures are less severe, but if we can't tell the arms what to do, then we can't complete the mission. Another big concern is cold welding. So what if you have 2 similar metals, will they fuse together and stop the arms from working? Motor failure is another one, although it has been mitigated because we have multiple arms, and then tool set failure. So if we move on to the next slide, we characterize them using a risk matrix. Our most severe, like I was talking about earlier, is the computer failure, but we're trying to mitigate this using 2 different GNC systems, one attached to the bus itself, and then one separate for the arms. Ideally, the ones with the arms would run the arms themselves, and then we would use the bus GNC system as backup if absolutely necessary. Again, we were concerned about cold welding as well, so to mitigate that, we use dissimilar metals, and we will use coatings as well to help stop the cold welding effects. Tool set failure is not a big concern for us as we have multiple tools, but we still need to design them in a way that will make sure that they can operate whenever they're performing their operations. Next slide. Finally, for a path to PDR, to move on to further development, we need to complete our analyses in thermal vacuum testing, and we need to before we build a prototype, we need to finish the dynamics modeling
including inverse kinematics, and then perform more FEA analysis. So, next slide. Finally, I'm going to hand it off to my friend Jake to talk about the design animations.
All right, so if you go to the next slide, here we have our full assembly CAD model integrated with the H.A.D.E.S Venus class bus. And we weren't given a CAD model for the bus, so we got a little creative and we used images of the bus, and we took the 15-inch Esper ring on the top of the bus and used that as a reference with pictures of the BCT bus. And then we're using that to get the correct dimensions and modeling a rough CAD model of the bus. If you go to the next slide, there we can see the zoomed in version of the tool belt. So we have 5 open slots on both sides. In this instance, we have 5 identical tools on each side, but depending on the missions, you could have up to 10 different types of tools. And next to each slot, you can see the box, which is the solenoid. These are linear pole solenoids. That's important because when we have no power going to them, we want them to be locked in place so that none of the tools are flying out or are able to escape. And then when power is applied, the solenoids are able to retract and the tools can be unlocked when needed. So going to the next slide. Here we have a CAD animation of a section view of the hand coming in and locking into a tool. And then it's the same process in reverse. For unlocking, the tool comes in, the solenoid will be locked onto the tool belt, and then the wrist is able to detach with the solenoid on the hand. All right, going to the next slide. Here we have an example of an object manipulation using our Rubik's Cube for our initial design. And so the hands are able to come in, grab the Rubik's Cube, second hand is able to come in, grab the Rubik's Cube and turn it. That's just an example of manipulating an object. You can see as this can go further, as the arm is able to swap in different tools, and as one arm holds the satellite steady, then the other arm is able to come in and perform different servicing operations. Next slide. So here we did forward kinematic analysis on our robotic arm designs. So we looked at different designs and looked at the range of motions of the arms based on the degrees of freedoms. And our current design is in the middle with the second picture. So the blue bubble shows the range of motion for one of the front arms, and then the red bubble shows the range of motion for that second arm in the back. And where those bubbles intersect is where we want to perform the servicing, as both arms are able to reach that section. Next slide. Here's our storyboard for our ConOps. So after launch, the satellite will be deployed into low Earth orbit, ideally with a target object in mind. And then once the satellite is able to be targeted, the arms are able to move to it and grab and hold on to the object and articulate it. Then once either scanning is done, if it needed, if the issue before is known, then we can just change the tools of what we already know we need to do. But if not, if it's an unknown satellite, we can scan with a camera with the second arm and develop a automated response so that we can identify what tools are necessary and what we need to change to. Then once the tools are able to be selected, the ISAM capabilities will be performed, and then multiple missions will be able to be carried out for the satellite's lifespan, and then eventually after its few-year lifespan, it will eventually fall into a decay and burn up in the atmosphere. Next slide. So going on to our prototype, we have a prototype here that you guys can take a look at. So we did a prototype of the hand design, and we felt that this is an important aspect of the prototype, as we need to have the 4 fingers able to close and open using the rotational motion of the motors. So with the rotational motor inside the wrist, the fingers are able to open and close. And this was just a rough 3D printed mock-up of the design. Next slide. So going on to data handling and communications. So for the automated ISAM operations and inspection, they don't require any real downtime links. However, if the satellite is unknown and we have to scan it prior to this, we'll need to scan it and then connect to a ground station to be able to receive that data and then send a command of what operations need to be completed based on the necessary servicing. And here you can see the uplink and download speeds of the different operations that we have. Next slide. So for the innovative concepts, the obviously obvious one is the interchangeability of the tool attachments and being able to do a specific task as opposed to just generalized service. So you could have a custom tool manufactured for a specific satellite and it can be flown up on the bus and be able to complete this specific servicing mission. And scaling the robotic arm system for small satellites makes the precision servicing feasible for other missions. So with the size of the arm and the bus, we're able to service small satellites such as 1U, 2U CubeSats, and many of the satellites that are already in low Earth orbit. And incorporating autonomy allows it to operate without any human intervention. Obviously, some human intervention will be needed to either abort missions or upload different commands of what operations need to be completed, but the arms will be able to communicate and operate autonomously during the servicing. Next slide. Now, the technology gaps, there's the accurate machine learning identification of different tools, parts, or satellite damage. So obviously scanning and rendering the satellite that we're operating on is a big challenge, and identifying what needs to be serviced and how it can be fixed. For it to be autonomous would be, you need a large program to be able to identify that, and precise control systems for robotics in space. So with the 6 degrees of freedoms, we have a complex geometry, and we're able to perform a forward kinematic analysis to get the range of motion, but eventually you want to do inverse kinematic analysis and determine the full capabilities of the arms and what they're able to do. And then the stepper motors lifespans is a big technology gap. So right now, the stepper motors we're using are space grade, but we have to look into more radiation hardening tools and stepper motors so that they can increase their possible lifespan and not wear out over the lifespan of the mission. Next slide. Some big challenges we encountered were the sizing of the stepper motors. So our initial design, the stepper motors didn't fit inside the joints that we had, so we had to extend the caps on each joint to fit space for the stepper motors and each of their encoders that are attached. And modeling the dynamics was a big challenge with the complexity of the arm and having 6 degrees of freedom, because the arm needed to be capable of linear motion near the bottom of the satellite so that it could be able to swap in and out tools. And then the data processing and transmission is a big challenge, because we'll have data for each stepper motor and the data for each from the cameras and the sensors on board, and all this needs to be processed in-house on the bus so that the arms are able to communicate and operate autonomously for their mission. Next slide. So we wrote a paper going over the purpose and the motivation behind our design, and it overviews the design of the arms, some potential tools that could be used, and their various applications. Now, future testing of the design needs to be done, such as vibe testing to survive launch, and other thermal analyses on the design. The paper details the risk mitigation and the prototype and development budget that we have. And we submitted this paper to the 39th annual SmallSat conference down in Utah, August this year, so we'll be presenting the paper along with a poster there. Next slide. So concluding our presentation, our Gator Arms is a small-scale autonomous arm system with interchangeable end effectors for in-space servicing, assembly, and manufacturing missions. And since we formed a team, we down-selected from over 30 ideas and included our systems requirement review, conducted various trade studies on our arms designs, and iteratively designed the Gator Arms. We conducted structural, mechanical, thermal, and kinematic analyses, and submitted the paper to the Utah SmallSat conference. And then we just submitted it to the NASA Tech Leap Challenge, where we hope to get approval and attain funding for further development of the design. Now, in the future, we hope to continue this design and continue work on the project, and hopefully raise the TRL level through prototypes and laboratory testing. Next slide. All right, thank you guys for your time. Are there any questions?
All right, judges, do you guys have any questions?
Yeah, Vinego here. I didn't quite understand the key differentiators of what you're proposing versus what's out there? Is there a way you can kind of summarize quickly?
So I'll use the example of Prometheus earlier. Basically, if you want to do an ICM mission using a CubeSat or a small satellite, we can't stick this massive 1,000-pound robotic arm designed for a geostationary satellite on there. We can't scale it down either, so we need to design from the ground up a better system that can be able to be used as a system architecture for that mission. So we can integrate to other missions as well as perform servicing.
But your analysis was cool for your workspace. Did you consider putting the solar arrays at the bottom? Because it seems like right here where the arm is, it might be a lot of
So the question was, do you consider putting the solar arrays on the bottom of the bus? We did, but we took the BCG-XS Venus class bus as it is, as gospel. So we didn't move that around. The actual positioning of the arms is variable, but we chose that as it seemed most intuitive, and it gave us that positioning on the top without having any potential conflicts or collisions between the arms themselves.
Because the thruster's on the bottom, I assume, like where the tool belt is that where the?
Yeah, so we based it off the VCT XF bus. So we just picked the optimal spots based on that bus, but I'm sure a more optimal bus for this design could be manufactured.
One more question.
Okay.
Could you go back to the command and data handling?
Can we go back to the data command and handling slide? Thank you.
Yeah, did you guys actually find or explore any sort of tactile sensors?
We did. So the question was, did you find or explore any tactile sensors? Yes, we actually chose some tactile sensors. They were, if I'm not correct, piezoelectric. We do not have them on these slide decks though. But our end goal for the end effector hand is that it can be able to be swapped out with power and mechanical coupling so that we can run these sensors to the fingers, and then say you grab onto something, you know how hard you're grabbing onto, how much force. So if this thing's fragile, you don't break it. If it's a weak component or a failed component, you don't rip right through it.
And for the tool belt, are there any issues with having the tools like just exposed like that?
So
I can talk about it. So we went through a bunch of different designs for the tool belt, and this was just kind of the one we ended up on, but it could be modified. Right now, as its current state, the tools are exposed to the elements when they're stored, but it could be modified so that the width or the depth of the tool belt is more than it's housed inside.
Yes.
You accounted for sensors, right, to
Yes.
achieve your machine vision. But what about light sources to illuminate the workspace?
That's a good question. We didn't account as much for that. I think that's more of our future work, but it's foreseeable that the architecture could adapt that. We initially planned for, on the base of the wrist, near the interchangeable mechanism, we have a camera so that you can see what you're doing while you're interchanging or while you're performing your operations. So we could feasibly add a light there as well. And I think that makes logical sense.
Are there any questions online?
Are there any other questions online?
I mean, your example tool was a drill, but there didn't appear to be any mechanism to collect the chips, debris from the drilling process and such. So in addition, obviously there must be some sensors on the end of the arm to judge distances and whatnot, but you may need communications and or additional power for whatever the random end effectors that you may need in the future. It may be a laser scanner or whatever. It may need a high-speed data rate or something. So I'm just curious whether you have options or growth or thought to those kinds of things. Over.
I think regarding that, we chose an off-the-shelf camera, but it is hard to find bit rates and for uplink and downlink. So I think that's more of our future work. But yes, foreseeably we would have included in the electrical connections, ways to send and receive data to the arms and get feedback from there.
I think that is time. So let's thank the GatorChomp team. And you guys should get to the front for your photo while the judges record the score and we get ready for the next team, which will be online. So yeah, that's the Venus Visionaries, another team from Penn State. They'll be up in just 2 minutes. Hey, Venus Visionaries, you guys can get started with Nebula when you're ready.
Thank you. So yeah, we're the Venus Visionaries, and this is all of our work as we have done so far for our planned nebular debris removal mission. Next slide, please. So an overview of our team. I'm Joshua Custer, the team lead. With me on the team is Aditi Priyasamanathan, Adab Driver, Zachary Kemper, and Shadil Sharma. And that's our DevBlock team. Next slide, please. So when we first just came up with the idea for this mission, the thing that popped up to us the most in research was the need for debris removal. Current projections show that Leo will be completely unusable within a few decades due to debris, and this will be caused by a phenomenon called Kessler syndrome, in which debris might collide with a satellite and end up releasing more debris in a never-ending cascade. To alleviate these issues, we are trying to demonstrate the autonomous rendezvous and deorbit of AeroCube 6b. This is a half-U CubeSat that is no longer functional. We chose it because it was small enough that we can easily design around the Venus-class payloads, but the 98-degree inclination orbit that it's in provided other mission challenges to show rigor in the design. We're going to be able to do this by performing proximity operations in day or night, and then we're going to use our new system, the JAV, to deorbit AeroCube 6b, and then we're going to recover and reset this so we can possibly use it multiple times on AeroCube 6b or on other satellites. Next slide, please.
And here is an outline of our system engineering milestones, with the most significant being our system requirements review in December of last year and the concept design review in March of this year. Next slide, please.
During the preliminary design phase, we came up with 3 innovative concepts that could accomplish our mission. The first was a net capture system, where we launch the net out, it encapsulates the debris, reels it back in, transports it to its new orbit, and then releases it. Next was the claw capture system, which was pretty similar, but it used a robotic arm that extended, grabbed the debris, transported it to its new orbit, and then released. And last was the junk annihilation vehicle, which we will call JAV from here on out. This was the most innovative concept. It was based on a harpoon, but instead of actually puncturing through the debris, we instead just hit the debris, transfer energy to it, slow it down so that it can change its orbit while we reel back in. Next slide, please. And then with these 3 concepts, we did a down select through a trait study based on criteria and waiting for our specific mission. And we determined that the JAV was the best option to go with for our mission. Next slide, please.
So this is an overview of what we think the entire mission will do. It'll begin with Nebular beginning in a parking orbit near AeroCube 6b. It'll use that to initialize all the systems. From there, we'll do a orbital rendezvous with AirCube 6B, mostly using ground-based data sent through communications. And then once we're within range of our onboard sensors, we're then going to transition to using those for proximity operations. Within about 5 kilometers, we can use a LiDAR system to assist. On 250 meters, we can use another camera to assist the LiDAR. Within 150 meters, we can use an infrared camera to track it at night. And then within 50 meters, we can use stereoscopic cameras to better determine the range and determine the spin rate of AirCube 6B. Proximity operations will continue until we are within about 10 meters of AirCube 6B. This is the range we determined for the JAV. And during this phase, the key parts of this phase, there will be an observer to make sure that everything is going well and that if something was to go wrong, they can provide an abort command. Before we transition to using the JAV, that same observer will also make sure that all systems are working, and then the JAV will then deorbit the debris. After that point, Nebula can return to a parking orbit to potentially deorbit a different satellite, or if it cannot do that, it can perform its own end of life. Next slide, please.
Focusing on the storyboard for the JAV itself, following proximity operations when we're in range to the debris that we want to be in, we will compress the spring that launches the JAV to the distance required for the velocity we want to launch at. Once it reaches this compression, we will release the spring, launch the JAV. It'll impact the debris, transfer its energy, slow it down, change its orbit, and then we will reel the JAV back in with its tether. We also determined that to get the total delta V that we want to achieve to deorbit the debris, we need to do multiple hits. So following this, we'll go back to prox ops, perform them again to get in range to the debris that we want to be in, and then perform additional hits as needed. Next slide, please.
So here's a 3D CAD model of our payload design. On the left-hand side, you'll see an isometric type view. And then on the right, you'll see a top view and 2 side cross-section views of the payload. On the top face of the payload, you'll see our cameras and our sensors. So in the corners of our stereoscopic cameras, they're placed as far apart as possible to enhance binocular vision. In between those is our LiDAR sensor. And then on the opposite end is the long-range and IR cameras placed next to each other for symmetry purposes. In the middle of our payload, in the center, is our chamber. And this is where the JAV projectile itself rests inside, which you can see in the cross-section views. And you'll see there's ball bearings around the JAV that helps with the alignment of it and to reel it back in more successfully. Underneath that is a spring that it'll rest on for launch, and it's connected to a tether on the tail end, which goes underneath where the winch is that will reel in the tether for the JAV. Next slide, please. Here's our 3D view of our design. Several dimensions that I'd like to mention. First is a payload. The exact dimensions are listed on the right side here, but that's the criteria we were given. But the JAV projectile itself, it's only 6 centimeters in diameter and 17.4 centimeters in length. So it is quite small. It's a lot smaller than we originally anticipated when conceptualizing the design here. And the JAV is connected to the tether, like I mentioned before. It's 15 meters in length and 1 centimeter in diameter, so it is quite thin. And the winch underneath the JAV, where the spring is, it's custom built in size to accommodate for 1 single layer of tether wrapping. That way we can minimize any jamming or unforeseen problems during launch. And that winch itself is 19.7 centimeters in length and 18 centimeters in diameter. Next slide, please.
Okay, so into more of the payload design. For proximity operations, when we were deciding which sensors we had, we looked at initially 3 different pairings. We had stereoscopic and LiDAR, thermal imaging with radar, and then a regular optical camera with hyperspectral imaging. We put that through the trade study, which is shown in the table on the right. We looked at size, weight, power, and the maximum range. Determined that the stereoscopic and the LiDAR would be the best. But in addition to those 2 sensors, we also added on the long-range camera to assist the LiDAR and the infrared camera so we can see things at night. Next slide, please. This is a more detailed view of how we plan to use the sensors at different ranges. The range with the LiDAR is a manufacturer-given spec. The others we determined through our own analysis by examining focal length, sensor size, and resolution. Within the day operation, there's a lot of overlap to ensure that we have redundancy and to make sure that we have consistent data when transitioning between the sensors. The infrared camera is the only one that can be used at night. it's not possible to do the sort of proximity operations that we intend to do with only that sensor. So it's mainly just used to keep track of AeroCube 6B in night until it's back into the day, so that way the day sensors can more rapidly reacquire it. Next slide, please.
For the JAV design itself, we first did orbital analysis of the AeroCube 6B. We did this to find the velocity it will be traveling at when we make impact with it, with the JAV. We also determined that we wanted to move it to an orbit of 300-kilometer altitude, mostly just because debris at this altitude does deorbit within a few months. From there, we were able to determine the delta V we needed to achieve this orbit transfer. With that delta V, we also iterated over different masses of the JAV that we can make it versus the initial velocity that we would have to launch the JAV at, which is shown in the figure there to the left. As you can see, at about 2 kilograms, the initial launch velocity of the JAV pretty much begins to plateau. So we decided 2 kilograms would be a good mass to make the JAV. From there, we also looked into the spring for launching the JAV, just based on volume constraints and the velocity we wanted to achieve. Once we determined the spring, we were able to determine that it launched at a maximum velocity of 9.7 meters per second. And again, like we said, this means we will have to do multiple hits in order to fully achieve the delta V that we want. Next slide, please. From here, we did focus on the material of the JAV itself. So we knew we wanted enough energy transfer to the debris in order to deorbit it, but we didn't want to just create a heavy, high-density material that would just break the debris on impact. So we decided the best option was a flexible frontal impact surface with a heavier density backing to it. To determine the specific materials for this, we did 2 trade studies for each of those components. The first one for the density backing is shown here on the right, and then the second one is shown on the next slide. But we determined that the best options were the titanium alloy and then a silicone rubber for the impact surface. After that, we did puncturing power analysis, the cross-sectional area that we needed so that it would not puncture right through the debris. We applied a factor of safety to this cross-sectional area to determine the one we wanted to use in our design. And then with this cross-sectional area, the densities for the JAV materials and the mass of the JAV, we then worked out the rest of the dimensions. We also looked into the tether, so we decided the best option for that would be braided Kevlar for its high strength, which, as Nadav said, we would be using a winch system for reeling that back in. We also analyzed the case if the JAV were to miss the AeroCube 6B and the tether became taut. We made sure the cross-sectional area that we made the tether was large enough so that it would be able to withstand the shock force in this case. And lastly, we looked into an alignment system to keep the JAV with the pointing accuracy that we wanted it to have. The option for this was a ceramic ball bearing option. It consists of 6 ceramic balls surrounding the JAV, keeping it straight so that it hits where we want it to hit. And we would be using a space-grade lubricant in order to allow for free rolling of the balls and mitigating frictional effects it has on the JAV itself. Next slide, please. Here is the trade study that we did for the impact surface of the JAV. Again, we did it based on things like tear strength, ductility, and it was determined that silicone rubber was the best option for that frontal impact surface. Next slide, please.
So here's the animation of our payload design. If you click it, yep, so you'll see the winch will reel back the JAV onto the spring so it loads for launch. It'll be launched out, and then once it hits the debris, it'll simply be reeled back in using the winch for relaunch. Next slide, please. So this is our mass budget of our design. So we split this into the bus and payload totals. The bus itself will be a total of 123 kilograms, and the payload, using our JAV and ProxOps weights and structure, will be 24.6 kilograms out of the 70 kilograms that we were allowed. Have plenty of space. Next slide, please. Our power budget, we divided this into day and night values with max and min also. And this has a 20% margin to account for anything extra, but our max amount of power usage will be during the day at 282 watts out of the 444 allowed. Next slide, please.
So to further verify that the power would work even in eclipse, we modeled this through the time of Aerocube 6B's orbit when it's in eclipse for longest out of the day. The net power shown in the black is the difference between how much power is needed and how much is actually being produced by the solar panels and the batteries, and it never goes negative, so we never have any concerns with that. Next slide, please.
The ground system that we are going to use is the Swedish SSC ground system. It features a 15-meter high gain antenna designed for reliable and cost-effective purposes. This setup ensures low operational costs compared to larger networks, and it can operate semi-autonomously, allowing mission controllers who are in ground stations to abort or to adjust operations if necessary. Next slide, please. Here is the flowchart of the command of how the command would go from the ground station to all the different substations. As we can see here, the CNDH, or the command and data handling, is the central nervous system of the whole communication architecture. Next slide, please. Finally, the communication requirements we specified that we want only 1 kbps over S-band, which is 2.2 gigahertz for commands, and 100 kbps for downlink over X-band for high-speed telemetry. This system uses 500 watts total transmission power for uplink and 5 watts for downlink. This link margins also ensure reliability despite the space loss and also signal degradation in low Earth orbit. Next slide, please.
So for our launch vehicle, we've selected Rocket Lab Neutron, a reusable medium lift rocket with a carbon composite structure. This vehicle strikes the right balance between performance, cost efficiency, and sustainability for our mission. It is compatible with ESPA ring integration, which simplifies payload mounting and enhances mission adaptability. Neutron also provides a strong operational flexibility, including a dedicated launch scheduling and customizable profiles, which is essential for Nebular's unique retrograde orbit requirements. While Neutron's first flight is slated for 2025, we're confident in its potential due to Rocket Lab's demonstrated reliability with the Electron rocket. Next slide, please. Here we've identified 4 key risks to Nebular's mission and outlined their mitigations. Our first risk is our JAV-HIT misaligning. This risk involves potential targeting errors. We mitigate this by implementing a pointing error budget and correction system. Our second risk is LiDAR failure, which can hinder navigation. To address this, we include a long-range camera as a backup. Third, we have our JAV tether braking. This could cause a loss of the JAV. We reduce this risk by calibrating the launch velocity to be low enough. Finally, proximity collision, a concern when operating in close quarters. We mitigate this by operating sensors below their maximum range to ensure accurate data. Each of these mitigations helps reduce the likelihood of impact of mission failure. Next slide, please. This risk matrix visually represents the severity and likelihood of each risk. For our JAV-HIT misalignment, we initially had it at a moderate likelihood and a low disaster level, but with mitigation, it's brought down to a low likelihood and minor impact. LiDAR failure was considered a moderate risk, and while its likelihood is still moderate, mitigation tactics keep the disaster level manageable. JAV tether braking was a high disaster concern, but mitigations significantly reduce its likelihood. And proximity collision was also on the disaster scale, but now it's much less likely thanks to operational safeguards. Overall, through proper risk assessment and targeted mitigations, we brought all key risks into the acceptable zone. Next slide, please.
The primary challenge we encountered with the proximity sensor ranges was that it was incredibly difficult to detect a 0.5U CubeSat using just cameras at a far range. This led to us reworking the entire suite to remove far range cameras, instead use LiDAR for long-range target acquisition. The primary challenge for the jab system arose from the necessity to fire the jab at a high enough velocity to impart enough momentum onto the aerocube while ensuring that its velocity isn't too high that the aerocube is unable to withstand the stresses that are imparted onto it. And finally, due to the aerocube 6B being in a polar orbit, it's impossible to maintain a constant communication uptime using just one ground system. And it's ideal to have a constant communication uptime so we could abort during proximity operations if necessary. This is a global system to maintain a near constant communication uplink. Next slide, please. For our camera observation technology gap, this follows very closely to our challenge encountered in that there simply exists no camera that's able to detect a 0.5U CubeSat at such far ranges, which would limit our ability to approach without using ground-based observations. For the JAV system, it's necessary to achieve a very high pointing accuracy with minimal friction to prevent any friction welding from occurring. We were unable to come up with an efficient method to achieve this. The current method we came up with is rather clunky and unverified. And finally, thruster efficiency is going to be the primary factor that limits how many missions or how many pieces of debris we're able to deorbit. This comes from the fact that propellant is really the only material consumed, making it the limiting factor. Next slide, please. This is some information about our paper, which was written to accommodate the 2026 AIAA SciTech Conference in Orlando, Florida. Next slide, please.
Okay, so when moving this design to the preliminary design review, we've outlined these 5 steps to take. First is to finalize the selection of components for the payload and other subsystems. We have selected some preliminary components for our preliminary analysis, but we have to make sure that those will actually suffice for all the requirements that we have. To make sure that can happen, we have to develop in simulations and other prototypes to make sure that we can actually use those to better verify the requirements than we can through just our mathematical analysis. And the last thing is to make sure that all these different things can be properly integrated within the bus. We already have them verified to a light degree, but making sure also that they can actually interact well with each other. Next slide, please. So more about the different components we have worked with so far. For proximity operations, we have 3 visible light cameras, 1 infrared camera, 2 long-range lenses, 2 short-range lenses, and a LiDAR system.
For the JAV, we have the titanium alloy, the silicone rubber frontal impact surface, the braided Kevlar tether, the winch system, the ceramic balls for precision, and then the spring for launching. Next slide, please.
So the power system is just based on the standard for the Venus bus. We're going to be using the dual array and a standard battery, and we plan to operate that at 28 volts. The GNC system, which is mostly the attitude determination control system, will have 2 star trackers, 4 reaction wheels, 3 torque rods, and a computer.
For thermal subsystem, we did heat transfer analysis to the bus and then determined the thermal control systems we needed to keep our systems in range. Next slide, please. For the structure subsystem, we looked at the vibrations experienced during launch. We used an aluminum alloy chassis with honeycomb cores, determined the stresses the bus would experience during launch, and made sure that it wouldn't, we could withstand these.
It's important to note that the propulsion system's only goal is to complete transfers. Attitude control will be solely handled by the GNC system. With that being said, the propulsion system carries 4 Aerojet Rocketdyne MR-103G thrusters, which are going to utilize 40 kilograms of hydrazine stored in Northrop Grumman 80304-1 propellant management devices.
For the command and data handling subsystem, we use an ISIS IOBC onboarding computer. Our memory and storage is a combination of MRAM and flash. And our communication interface is a combination of 12C, UART, and SPI protocols. That just enhances any flexibility and reliability of the system. Next slide, please.
From a technical perspective, the JAV offers significant advantages to the space industry. Most critically, future satellites may no longer need an onboard deorbit system, which translates to weight reduction, simplified design requirements, and ultimately cost saving for satellite manufacturers. Additionally, our system provides a safety net for existing satellites in cases where their native deorbit system fail or become inoperable. This offers an important redundancy option for the growing satellite population already in orbit. What makes our approach innovative is its harpoon-based hit mechanism, which represents a novel concept in the debris removal field. We've designed the JAV to be reusable and adaptive to different satellite configuration and sizes, maximizing its utility across various mission profiles. Next slide, please.
Okay, so with all the analysis we have done so far, we believe that the JAV can be a simple and effective way of reducing the current debris problem and assisting in preventing it in the future. Because it's mostly from off-the-shelf components, we believe that it is feasible to make this by the early 2030s. The main thing that has to be done is to make sure that the JAV can be designed and operate properly. And so overall, space debris is an issue that has to be dealt with. The nebular demonstration can show a way to mitigate the current issue and help prevent it later. Thank you. Next slide, please.
Okay. Do you have any questions from the judges? So I have one question just to get started. How are you going to hit it more than once?
So after the first hit, we will analyze the debris again, figure out the new orbit that it has transferred to, and then we will go back to the proximity operations and perform those so that we can get back in range to the debris, back in range to its new orbit, so that we can do the second hit and further as we need, and then again perform the same JAV storyboard operations that was shown earlier, and hit again for however many times we need to achieve the total delta V that we need.
And related question is, do you think it's viable to get it to a low enough orbit with one good hit?
I feel like that would be related to scalability of the mission too. So of course, a larger JAV is able to have a higher energy transfer and give a higher delta V to the debris in order to change its hit. So I feel like in the future with a larger JAV and a bigger operation, that possible in order to achieve it with just one hit.
If you can't do it with just one hit, then you're chasing it as it gets closer and closer to Earth, and you are expending more and more propellant to be able to pull yourself out of that altitude, right?
Yeah. So in that case, the additional hits will actually be performed within a few minutes of the first hit. So we aren't going to be falling all the way to its new orbit and hitting again once it's on the new orbit after the first hit. We'll fall immediately after our first hit to get back in range of the debris, form the and then go from there. And also, that's another reason it's good that we have low consumption already, because in that case, when we do have to follow the debris, we have plenty of fuel available in order to chase after it and get back in range for additional hits.
I can't wrap my head around something. So you have a mass of 2 kilograms traveling at 30 meters per second. That has the kinetic energy of a small caliber bullet. How do you make sure that you don't break up the satellite you're trying to deorbit into smaller pieces and making the problem a lot bigger than you started with?
That was through the JAV design itself. So again, the frontal impact surface, we looked at materials that were very flexible so that it doesn't so that it's able to deform when it hits the debris and then form around it in order to not break anything off. Additionally, we will be hitting on a surface that's doesn't have high risk objects on it, so that we don't break that off. And then again, the puncturing power analysis that we did was we determined the cross-sectional area that we would have to make the JAV so that it wouldn't actually break right through it again. And then we also applied a factor of safety just for safety.
So does that assume that your target is a solid metal or some kind of material?
Yeah. So right now it assumes that the face is flat, which we did go through. You go to slide 36 if you would, please. So as you can see here, we did look at the debris that we're hitting right now. The one side has high risk pieces on it that would break off if we hit it, but then the other side with the target area is pretty flat with not much there. So that's what we were basing our hit on, would be the surface that doesn't have much high risk objects on it, so that we don't create more debris during our deorbit mission.
Okay, and I think that's all the time we have for these guys. Thank you, Venus Visionaries, and good luck. And we have 2 minutes, and we'll do the next team in about just 1:36.
Thank you.
Okay, while we wait for the last team to get started, I just want to say that it's been a very intense 3 days for myself and some of the others who've been here. I've been absolutely blown away by how strong these teams are. I haven't seen like one clunker, to be honest. They're all good. Most are great, and there's a few that are absolutely amazing. So I just want to say that to everyone's still here, everyone here today, everyone there at Goddard. You guys have done a lot of hard work, and you should be very proud. We're going to do this again next year. If you're still in school, you're welcome to form a new team. You're welcome to mentor your old classmates. We really want to hear from you. You're not going to hurt my feelings if you tell me what we did wrong. In fact, I'd much rather hear what I did wrong than 60 emails saying you did a great job. Those are fine too, but please be open with feedback. So with that, we're gonna kick off the last presentation from the Stellar Solutions at Penn State University, Project Starforge, and you have the floor.
Good afternoon, everyone. We are Stellar Solutions from Penn State, and this is our final outbrief. Next slide. Next slide. So a quick summary of our mission. We're calling it Project Skyforge, where we are going to melt a material in space and then inject it into a mold and then cool that material. So we wanted to do this because current missions, and we have some plans that show promise with extracting materials from lunar regolith and asteroid regolith. There's a few methods that are defined for tuning the extracted materials into useful products already. So we aim to further develop this inner space manufacturing capability by utilizing a payload that turns the regolith into a rod-like structure. And we chose a rod just because they're very common in trusses and other structures in orbit already. So we could make them there rather than on Earth and not have to burn fuel to send them up. The technology for this mission mostly exists already. It's just never been used in a way we want to use it so far. So that's what we plan on doing, just adapting current technologies for use in space. Next slide. So this is our team. We have Avi, Connell, Brendan, myself, Cole, Dan, Mike, and Alec. Alec graduated, so he's not here anymore, but he's still a part of it. Our advisor, Professor Lego, and our mentor, Gregory Richardson. Next slide.
Looking at our process of systems engineering, when we were first introduced to the project, there were a lot of unknowns that we had to figure out, and we had to go through the process very systematically. So our second week of the project, I was elected the program manager, and soon after that, we formulated 3 different solutions to this problem we've posed, creating ConOps for all 3 of them. We then moved to system requirements and further subsystem requirements. Eventually, we did a trade study for those 3 proposals and a number of other trade studies as we worked through the subsystem analysis. Then we came to a concept design finalization. That was just a few weeks ago. And here we are for the preliminary design review, going over our final results here and discussing our research. Slide, please.
We started off with thinking up 3 concepts, and the first one is levitation heating. It was an idea where we wanted to use induction coils to induce a magnetic field, which will levitate and melt the material. And then the material will be in a mold where it will like solidify and cool. And then a robotic arm will be used to transport the cartridge and mold within the payload into storage. Some of the lessons we learned from this concept was that the introduction of an arm creates more points of failure, since there's a lot of thermal requirements that we need to process and think about when making the arm. And we also learned that levitation increases risk of failure because of the fact that molten material, especially metal, is difficult to contain once the levitator is turned off. Slide, please.
Another concept that we considered was called a solar centrifuge. It uses the sunlight, and it is similar to concentrated solar thermal panels that we have today used for energy. What it does, it directs sunlight to a single focal point and then uses that thermal energy in conjunction with heating coils to heat the material. In conjunction with that, we have the centrifuge, which spins, introducing artificial gravity. Some lessons that we learned from that is artificial gravity, as far as the centrifuge, would not be as feasible if we're trying to transfer material. And then with that, all the moving parts would be complex, it would be expensive, and it's just not in our best interest. Next slide, please.
So for our third concept, we had the idea of injection molding, which in this concept, we used syringes, which were attached to a conveyor belt of sort that would move into the induction heating coil, and then that would melt the material, which then after that, it would move again to the mold, which this seemed like a pretty good idea, but we noted there's a large possibility for slag accumulation just because there's so many moving parts in this. We also noted that it's not really scalable since the syringes aren't reusable. We'd have to bring up a new syringe every single time we wanted to do it. And we wanted to prove that this was reusable for our mission. Next slide, please.
All right, so when comparing our 3 concepts, we conducted a trade study based on certain criteria that we thought were important. These included cost, reliability, thermal management, power consumption, scalability, complexity, design uncertainty, and technological maturity. And based off our trade study, we decided to move forward with the injection molding design. However, as you'll note later in the presentation, you'll see that our design did change quite a bit, and we also incorporated ideas from our other 2 concepts. Slide, please.
Moving on to our storyboard and ConOps. On the left is a general overview. On the right's a GIF, so if you miss a part, you can just loop on over and watch it again. We're going to start off with launching from Cape Canaveral using the SpaceX Falcon 9. This is useful for us due to its rideshare capabilities. From there on, we're going to model transferring pure material sample from another spacecraft. In our case, we're doing more of a proof of concept. Transferring material would be something that we could prove for scalability later if we wanted to. From there, we'll melt it and transfer the material to another spacecraft. After that, we're going to continue the process until its lifetime completion, and that'll be moving in semi-autonomous operations, which we'll define a little bit later on.
Next slide, please. Oh, okay. So before playing this video, I'll just give you some key points about our operating sequence. So first, you have our heating phase, which is where the induction coil is going to create a strong magnetic field. And then the electrical resistance is going to cause our material inside to heat to the point of melting. And inside, we're going to have an auger-like screw that'll be rotated by a DC motor. Then this auger screw will move the molten material axially through a valve into a series of molds. And within these molds, they are in a coolant chamber where they will be cooled and solidified. And finally, we'll have our extraction phase where we'll use a piston to eject the completed part. So if you want to go ahead and click play on that video.
You can advance the slide. I think that'll do it too.
Okay. There we go.
There we go.
All right, so here you have the interior of our syringe mechanism. We have our rotating auger screw. It's going to go through that valve into, this is our coolant tank. We have our revolving mold mechanism. And finally, we have our piston there ejecting where it would go out the backside. And then here you just have a 360 view of our payload. And that piping you see around our coolant tank is just our coolant fluid system, where you have a pump and a radiator on top as well. And yeah, you can move on to the next slide, please. So yeah, here is just a quick 3-view breakdown that we got from CAD of our payload. We have some just basic dimensions. Yeah, next slide, please. All right, so first talking about our mass budget. Key note here, as you can see from our total mass, it is 9.8 kilograms, which I'm sure you can see is quite low. The reasoning for this is because during initial conversations with our mentor, he suggested that we make our manufactured part pretty small. This is because increasing the mass of this part, or the mass of the material needed to be molten, would take up a lot of energy. So we decided to go with a small rod, which is actually about 8 centimeters long. And then we built the rest of our payload around that part. And so most of our parts ended up being quite small, which is why you end up with this lower mass. Most of the component masses were calculated using mass properties in SolidWorks, depending on the material assigned to that component. We also, for components such as pumps or the valve, we looked at what a standard component would weigh and then kind of scaled that down to the size that we were going to be using. And then for our coolant fluid, that mass was calculated using the calculated volume of the fluid flow region and then just multiplying that by the density of the coolant fluid. And we also gave the mass budget a 20% margin for error in the case of any of these estimates not being completely accurate.
Next up is the power budget with the payload power and the spacecraft power.
You may want to go back. That was on the same slide.
Yeah, sorry about that. All right. But most of our power was used for heating and mechanical components and also cooling, at least for the payload. And then for the spacecraft, the attitude control and the thermal aspect of the mission used up most of the power. And most of these calculations were made by using real-world examples, especially the heating and mechanical components and sensors. For the mechanical components and sensors, we found real-world examples like DC motors and thermal and pressure sensors to figure out how much power they would use on average. And then we calculated the numbers based off of that. And for the power needed for heating of materials, the metal and melting it, that was calculated using an induction heating power requirement calculator. And just like the mass budget, this was given a 20% margin, which is industry standard for a margin. Next slide.
So, quick little blurb about the thermal subsystem. These are two of our more important trade studies. On the top, we have what type of heat exchanger that we were going to use to cool it down. From the trade study, it showed that we were going to use a cross flow heat exchanger, which is what we had modeled in the CAD. And then on the bottom, that is the coolant we're going to use, which we ended up using a molten salt coolant called the Globaltherm OmniStore MS600, just because we had the realization that water and ethylene glycol, which are very common coolants on Earth, would not be able to handle the heat we're going to be generating. Since the metal is going to be up at 700 degrees C, they would have evaporated almost instantly, and that would have caused many problems. It's also important to note that we're not actually cooling the material down to room temperature. We only are going to go down to 400 C for this, just so it's solid, but it will still be pretty hot. Next slide, please.
All right, so just a quick overview of a little bit of a structural analysis. So on our left, we just have our bill of materials. That's all of our components that were used in payload. And on the right, we have a trade study that we performed for the material we're going to use for the exterior of our melting mechanism, so the outer shell. This was really important material because this is where the main thermal strain in our payload is going to happen. And so 3 materials that we identified as candidates were carbon phenolic composites, a titanium alloy, and silicon carbide, which is a ceramic matrix composite. So our 2 most heavily weighted criteria that we wanted to make sure are really strong were very low thermal conductivity and low coefficient of thermal expansion. And this is because we wanted to insulate as much heat as possible, because say while our satellite is in orbit away from the sun and we're not in a phase of heating, we want to contain as much heat as possible so our molten material doesn't solidify inside of the syringe. We also want low coefficient of thermal expansion because we want to limit the thermal deformation under these intense thermal loads, because that could cause potential component failure. And based off of the trade study, we went with the carbon phenolic composite. Next slide, please.
Okay, so as we were moving forward with this design, we came up with a couple of risks that would be possible here. First, I'm going to talk about slag, which is our worst risk, really. So there you can see on the right, it starts up in the red. So as Cole talked about earlier, slag is this molten material hardening within our syringe. This is bad. It could cause clogs, possible leaks, things like that. So mitigations, the syringe is constantly moving. Hopefully this wouldn't cause slag to accumulate. And also, as a part of our future work, we're talking about implementing a scraping mechanism to clean out this syringe after a mission. Second risk is our molten material leaking. Not super likely, but still not great. If it were to leak, it would leak into the coolant, which hopefully would get rid of all the heat from that. Third, we can have our mold get lodged in the chamber. So this is what our piston is for, to get the mold out of the chamber. But if this piston for some reason weren't be able to get it out, not a huge deal. We can just recover the mold later and remove it ourselves. And fourth, loss of power. This wouldn't be great because mainly it would lead to number 1. It would lead to slag generation. So as a part of our future work, we could talk about implementing a battery or something like that.
Next slide, please.
Moving on to data handling and communications. First, we'll be talking about the optometry associated with our project Skyforge. The main reason why we need optometry in this payload is because we're dealing with molten material. And as Mike said earlier, this is a big risk for us. We don't want any of that material leaking out. And we have a lot of mitigations to do so, but we also want to check via optometry that nothing is wrong structurally with our payload. To do this, we modeled the different points as far as line of sight data in STK. And we considered originally 3 ground stations, the one in Wallops Island, Virginia, one in White Sands, New Mexico, and a dedicated one in State College due to convenience. From this, we can see that the Wallops Island has the most amount of access points, as I've called it, which just means that it has the largest amount of times that it can see the payload in space. It also has the mean coverage time is about the best for Wallops Island. So that gives us a good idea of where we want our ground station to be as far as optometry goes. Next slide, please. As far as our communications equipment beyond optometry, we considered a link budget for all our near-Earth network systems at Wallops Island and White Sands. If there was any big idea to take from this, it's that our link margin, either uplink or downlink, is very big. So it's not going to be anything that's going to be restricting us. For our payload size, we're going to be using 0.05 meters. That's to give us enough space in the payload to do whatever we need to do. And as you can see for the bit rate calculation at the bottom center, it's not necessarily the calculation itself, it's some things that we took into account. One of them is for the orbit, and it accounts in case we want to scale up a little bit as far as transferring material to another spacecraft to include our autonomy. So we can definitely handle more autonomous features in this. We can send it basically into space, not worry about it unless there's an emergency. Next slide, please. Moving on to the technology gap assessment. One of the technologies that could help us is a high efficiency coil. As you can see on the bottom right, we have a picture depicting superconductivity. This is kind of relative. We do have superconductivity, but nothing that's very high temperature like what we would see in this payload. If we had something like this, we could more efficiently transfer power to and from the bus, the payload itself, wherever we need it. And the second one that we identified was ceramic composites. Some of the more advanced ceramic composites, as you can see on the chart on the top right with the red arrows, we have one that's porous and non-porous. They have a very high strength density ratio, which would be very good for us. On top of that, ceramics are very bad at conducting electricity, and they're pretty good at insulators for us. So this would work very well for some of our materials components. And finally, our space welding techniques. We have very small rods in our system, as we've mentioned several times before. If we had better ways of welding in space, this would give more relevance to our project and would make it very, very sought after in other teams. Next slide.
Okay, so challenges we came across during this mission. First, we're in a microgravity environment. This means it's not just like melting something on the ground and putting it in a mold. We had to deal with the side effects of being in microgravity. Second, our payload size is small. We would have liked our part to be bigger, but just because of the constraints of the payload, it's pretty small. And finally, determining a material for our rod, we wanted to make sure it occurred in asteroids in some capacity. And we also needed it to be magnetic. Next slide, please.
Coming to our paper, this talks about the research we've done in a lot more detail, especially in regard to the subsystems. We have an abstract of 169 words, 20 pages in length, and they pull from 14 sources. Looking at where we can present this, there is a small sat conference coming up in Salt Lake City next year that focuses on a lot of these CubeSat and small sat missions, very similar to ISAM, and we'd like to potentially present there and share a lot of the research we've done. Slide, please. Now looking at our path to PDR, we first start with the integration to the Venus bus. This helps us do a lot of the functions that the payload needs to complete, but it also presents a number of challenges as there are some unknowns about the Venus bus. Power was pretty easy to figure out because we can opt for the dual solar array that gives us 444 watts of steady state power during daytime operations on the day side of the planet. That accounts for about 60% of our orbit. As for the structure, we can mount this just about anywhere in conjunction with other payloads because of our small mass and volume. So that saves a lot of launch costs and makes the most use out of the spacecraft. In terms of attachment points, the interfaces on the Venus bus are unknown to us, but we can fortunately mount through any of the thermally stable components on the Skyforge payload. Things like our pumps, parts of our cooling system, or perhaps the carousel that holds the rods. All of these experience far lighter temperature swings compared to something like the auger or the induction coil. Now for communication, as Brendan discussed earlier, we can take advantage of some of the systems that we can expect on board the Venus bus. If this is similar to other small spacecraft in low Earth orbit, we anticipate a data rate of 5 kilobits per second, and that's for the engineering and health data. And then the figure for 10 kilobits per second, that happens because we add a little bit more for the science and information coming down from the payload, as well as our pressure and temperature sensors. As I said, that is based on assumptions of communication systems for low Earth orbit spacecraft of that size. And fortunately, we can take advantage of a lot of that. There's no real hang up there with the capabilities of the Venus bus. Slide, please. Now looking at our future work, as proud as we are of what we've researched for Skyforge so far, there's a lot more that we wanted to do and a lot of potential that still has to be investigated for this mission. First, backup batteries would tremendously expand our reliability. Not only could we run the payload on the night side of the planet, but if those dual solar arrays were to fail for whatever reason, we can take advantage of that battery and continue operating and complete our mission. Superconducting materials, of course, a really hot topic for research right now. Those would really expand the capability of Skyforge because we can use a lot less power and also get the same results. So that can expand a lot for what the mission can do. Slag removal, as Mike discussed before, that's really critical for ensuring our reliability, improving that. Imperfections in the rods that we create is really important because we're working with large thermal gradients in a vacuum. You can have issues with gas in that rod or some other things. We want to make sure that this is really structurally sound. Thermal insulators are really important for the entire payload, not only protecting sensitive electronics and equipment, but also making sure that the heat stays where it's supposed to be and makes us a little more energy efficient. Coming to our summary, our mission is to demonstrate metal injection in low Earth orbit.
Next slide.
Oh, next slide, please. Excuse me. Our mission is to demonstrate metal injection in low Earth orbit, which would be a milestone for space manufacturing. Other things have been tested, but this is where we really innovate here, using that power and injecting a hot metal material. This is going to have tremendous impact for the space industry in terms of construction and future science missions and lowering launch costs. And finally, our lessons learned is that this is a really difficult mission to pull off in terms of heat management and moving the material in that harsh microgravity environment, but we think we can make the most of it with the solutions we've developed. We're very proud of the work that we've accomplished in studying Skyforge, and we really think it holds a lot of promise for the future. And we're happy to take any questions that you may have.
All right, we have time for questions. So, you know, the the big challenge with any heating operation on orbit is removing the heat, right? And like it seems like one thing you did to do that was to limit the mass of the material that you're melting and injecting. But like, what kind of analysis have you done to see how that heat would dissipate over time in the satellite?
So I'd like to begin with a critical part of our orbit analysis. Actually, we've been looking at making the most, taking the greatest advantage of the power we have on the day side of the planet and then cooling on the night side. So we started our analysis with passive cooling there. We knew we were limited in energy and had to make the most of that. So the passive cooling gets us a little bit, and it really depends on the scale of the mission, exactly how fast that cooling happens and how much energy is removed. But of course, we're going to have some left. And at that point, we decided to add a radiator to that. And if you have some further questions about that, Avi, I think you were the one who did the sizing for the radiator.
That was me.
Yes. Cool.
Yeah, so as shown in the CAD, that radiator, I ran a couple SolidWorks simulations on just to see how long it would take that the actual rod to cool down from 700 degrees C passively, and then we found from that it would take a decently long time. So that's why we added the radiator, and the size was mainly based off of the size constraints that we had, and we didn't want to make it just too large and make all of our mass in the radiator. So that's kind of where that came from.
Okay, thank you. Do we have other questions from judges?
I have a couple of things. So have you considered the volume change between a liquid and solid, which would probably be significant on the order of 20% or so? So when you have a molten material and then you try to cool it, it will shrink. Does that affect your operation somehow?
Yes. Actually, this was taken into account when designing both the molds and the screwing mechanism. So the amount of our raw material is powderized aluminum, and I forget the exact number, but there was a few percentage point change in volume when solidifying, when first melting and then solidifying again. So then the size of the screw is actually greater by that value is calculated, but I don't have it at hand. Greater than the volume of the powderized aluminum that is already in the screw. So then when it's melted, it has room to expand, and then it's assuming that it will contract back down to the given volume of the rod that we had specified in our mold.
Yeah, thank you. That sounds good. I think you actually had a very good approach going small because of the power. Have you given any consideration of sintering as opposed to melting? That will save you power. Usually sintering happens at lower temperatures, and it doesn't have that problem with the volume changes.
Yeah, we were looking at addressing some of the sintering operations a little bit in the beginning. It wasn't one of our initial concepts because we looked at some of the structural integrity issues that might be risen when sintering is in operation. And we thought going through more of a typical route of melting would enhance this overall strength of the material.
Thank you.
You seem to be worried about slag in your system. Have you looked at whether slag will actually separate in microgravity? It probably will not rise to the surface because there's no gravity differential over.
We have looked at that somewhat. When we first started doing our Skyforge analysis, thinking about what materials we were going to use. Initially, we weren't sure. We thought we might do steel or something else. We found that aluminum is available in about 10% concentration at greatest in various asteroids in the belt. And we are assuming that some other mission or some other process has already refined that for us. We found that in working with imperfections, working with slag from other materials or elements could complicate the mission a lot and put us outside the scope of what we could study. So we've assumed that some other project could do that and therefore refine it. And then we are met with the pure or almost pure aluminum powder that then goes into the auger system.
Okay. And I think with that, we're going to say that we are at time. I want to thank our final team, Stellar Solutions with Project Skyforge. And yeah, everyone can, well, especially me, can kind of exhale. Judges, record your scores. Please send them to me. Well, you need to send them to me tonight so we can include them. We likely won't announce all the winners next week, but we will let you know if you've won a prize. And we'll handle the which prize a little bit later. And yeah, other than that, thank you very much. And Colleen, I'll turn it over to you and let you close this out.
Thank you. We are just starting to get packed up here at Goddard. So I'm just gonna, we're all getting ready to go. So thank you guys for coming in, and we hope you all have a great day. And we're gonna say goodbye here. So thank you guys.